Good morning.
Hello.
Hi. Well, good evening to you.
Yes. It's, what time is it over there?
My time, almost 9 o'clock in the morning.
Oof, that's early.
It's a nice hour for me. So Stephen is the chair. I am the help desk. I'll watch the help desk message and if needed, repost it.
Mildly worried that we haven't heard from our first speaker yet.
Yeah, me too.
Okay.
Ah, he's on his way.
Cool.
While we wait, Katarzyna, do you want to try to share your slides, do a little test?
Yes, I can do that. I can share my screen. And give me a second.
Yeah, sure.
Morning, everyone, or whatever time of day it is.
Morning.
Share your slides, do a little test.
Yes.
Ciao. Guarda,
I think.
So hello, can I share my screen?
Yes, go ahead, and then
Okay,
we'll do the test with Dimitri afterwards. Yeah, so we see.
Okay, so you can see my screen?
Yeah, we can see the window with the slide, with the thumbnails and all. So you probably want to go into presentation mode.
I have already presentation open.
Yes, go ahead. And then yeah, that works perfectly.
Okay, that's good. So maybe I will start.
Okay, and I will set Dimitri up. If you can stop sharing this. Yeah, thank you. Your turn, Dimitri.
You're muted, Dimitri, as well.
Oops, things move. There we go. Yeah.
Can you see it?
Yes, we see the browser. Is that what we're supposed to see? Yeah.
Yeah.
Yeah. Okay. That's
something
good.
like that. Great. Shall I leave it, or someone else wanted to check first?
Yeah, I think we're going to go to the starting soon screen, I believe, Francesco, for another few minutes.
Okay.
Thank you.
So we're at the top of the hour. Shall we start?
Yes, let me share my screen. Hope you
All
can see
right.
it.
Yep. So I'll just.
Nice.
So welcome to the last session of ADASS 2020. We have a few talks, and then we have the prize talk, and then we have some closing remarks. Our first talk is about machine learning for the Zwicky Transit Facility by Dmitry Duev, who is from Caltech and is giving the invited talk on this session. Take it away, Dmitry.
Thank you so much. Let me start by saying a few words of appreciation for the organizers of this conference. I've been really enjoying it. I'm really thankful for the invitation and for the for this possibility to talk to you. So I, as said, I'm a research scientist at the astronomy department at Caltech, and I'm going to talk about the machine learning applications for the Zwicky Transit facility. If for some reason you are not familiar with the Zwicky Transit facility, so it's I would say an industrial scale robotic optical sky survey that is using the 48-inch Schmidt telescope at Palomar Mountain in Southern California. It performs accurate measurements of billions of astronomical objects and registers an order of 1 million of transient events every night. So I'm not sure if you can see my mouse, but this is the Palomar Mountain. On the bottom right is the P48-inch telescope. That's how large the camera is. That's where it sits inside the 48-inch telescope tube with the robotic end that does the filter exchange, and this is the first light image of Andromeda. ZDF at a glance, very large camera. The active detect area 47 square degrees can in principle survey the full the entire northern sky that is visible from Palomar. Nominal exposure time in a nominal exposure time of 30 seconds, we get down to something like 20.5 at a in the R, the image quality of 2 arcsecond. So, main science drivers for ZTF have been the following, as many of you know. So it's we're interested in fast, young, and rare flux transients, looking for counterparts to gravitational wave sources, low Z type 1a supernovae for cosmology, all sorts of variables, variable star signs, eclipsing binaries, solar system objects. If you want to learn more, please go to our website. On this slide, it's kind of messy. I'm showing the data processing flow as of the end of the ZTF phase 1, which completed just a month ago, and we've entered phase 2 on October 1st for another 3 years of operation. The key point here is that there are all sorts of pipelines that produce all sorts of data products, such as the famous transient alerts, but then also streaks detected from fast-moving objects, photometric time series / light curves, and all those are consumed by a wide range of processes and services. Whichever way you look at this diagram, it is teeming with vast amounts of data and highly nonlinear mappings. And we all know that this is exactly where machine and deep learning excel. So what are we using machine and deep learning for? I will unfortunately not have the time to go over all applications, but I will put some of them in the spotlight in this talk. Among those are alert classification, identification of streaking near-Earth asteroids, then identification and localization of comets, classification of variable objects, classification of spectra taken with the SED machine, so the main workhorse that we've been using for classifying discoveries, supernova-like discoveries made with CTF. Then predicting behavior of AGN, fixing the focus model for the telescope itself, looking for all sorts of anomalies in all sorts of our data, deconvolving images in dense field, and the list goes on. Let me start with the famous transient alerts. So these little packets that we send out every night, and hundreds of thousands or like up to 1 million, that contain cutout images of the part of the sky where an event has happened, with a rolling 30-day window light curve or photometry history, plus a whole bunch of metadata, including some machine learning scores in there. We've been using a system called BRI, which stands for something like Bogus Real Adversarial AI, which is a CNN ConvNet-based real bogus classifier that yields something like an order of 1% false negative rate and false positive rate, and yields consistent performance across the phase space. Shifting gears back to our solar system, for the so many of you may know that the number of streaks that ZTF detects is every night, rather streak candidates, is essentially the same as the number of alerts that we produce, or even larger. But the number of false positives there is just astonishing. It's a couple orders of magnitude more than that for the alerts, and it's a challenging task to identify actual fast-moving objects or near-Earth objects among those. And for that, we're using a system called Deep Streaks, which uses an ensemble of ConvNet-based classifiers and achieves false negative and false positive rates that are well below 1%, which actually gives something like a 100x improvement over previous generation system that was deployed before we rolled this one out. To date, we've discovered over 180 near-Earth asteroids, some of them pretty interesting. And also should mention that the similar number was lost due to insufficient follow-up, because we tend to find fainter stuff that moves real fast, and it's real. If you don't follow it up in a timely manner, then that's it, it's gone. Till next time. Staying in the solar system, another system that I'm very excited about, we call TAILS, and we use it for deep learning assisted discovery of comets. It uses a state-of-the-art object detection neural architecture called efficient DET that we highly customized for this task. We've assembled a very large and diverse training data set as essentially in all other applications. And with the help of deep learning, active learning, sorry, have been able to achieve over 99% labeled prediction accuracy. So it looks at the images and tells you whether there's a comet and then in it, and then it also tells you where exactly it's located, and that is done with a precision of one to 2 pixel median positional root mean square error with respect to the nucleus position of comets as reported by JPL Horizons for known objects. We've been running it in production since late August this year, and it typically produces something like 10 to 20 nightly candidates. It works on stacks of images, either just science reference and difference image for a given patch of sky. But then we've actually found out that it works as well if you ditch the difference image, so no difference image required for the same kind of performance. very exciting. We just we got our first AI-assisted comet discovery last month. C2020 T2 discovered on October 7 in the twilight survey data of ZTF. It's just a very nice demonstration of the fact that this stuff works really well, and we're looking forward for more discoveries. Shifting gears again, let me talk a little bit about the project we've spent quite a bit of time this year on. It's called SCOPE, which is some sort of an acronym for the ZTF Variable Source Classification Project. And we've started off with a pilot study. We selected 20 fields that are kind of representative of what ZTF is looking at, with 34 million objects in them. We've done a lot of work on the features, nomenclature, data assembly, data set labeling, and so on. And I'll go over all these points in the next slides. The key point here is that we are building in this project, one of the things we're doing is we're building labeled data sets and machine learning pipelines that are now being scaled and extended to the entire ZTF data. First publication is out, and the second one is currently under review, so I'm expecting it to be published very soon as well. Few words about the nomenclature and the classification scheme. We've spent quite a bit of time figuring out how to do that best, and what we converged on is a scheme where we separate the phenomenological and what we call ontological classes. And so in the first case, basically those classes tell you, in those classes, it's everything that can be said about a source given just the ZTF data. And in the second case, not just the ZTF data. And the classes and labels we organized in a tree-like structure, but each leaf of that tree we treat independently. So we get a set of independent binary classifiers. Essentially, every one of them tells you how likely is that this particular source is of class X. And it actually gives you quite a bit of power in that if you know that the performance for one particular class is not great, you can tune and improve it without affecting the performance for other classes for which you're happy with the performance. We've selected a subset of the full class tree for this pilot project, and I'm showing it here on the bottom right. And another nice feature of that scheme is that you essentially get anomaly detection out of the box. So by playing around with these range sliders, sort of, we've been able to find lots and lots of very interesting objects. We've been using a set of features for classification. So all light curves with at least 50 epochs for now in those selected fields have been period searched using these three algorithms, for all of which we now have a very efficient GPU implementation. Plus, we've been using a system called Kowalski to feed in the data, and I'll talk a little bit about Kowalski at the end of my presentation. And that approach delivers scalability, and essentially now we've done the same for the full ZTF data set as it is of now. We've been using respectable, I would call it, variability features. See a paper from Kirill Sokolovsky from 2016. We've also been using graphical representations of the light curves themselves, condensed into this second order characteristic of them, the MDTs. and we've cross-matched all that data with 10 external catalogs, and that's the data that is fed into the classifiers. Labeling all that data is no small task, and we've built quite a few interfaces for data labeling and exploration, and I'm showing some of the examples here. So you need something that is fast and API driven, and also provides you interactive access to all sorts of information about sources in bulk. And this has resulted in one of the, I guess, largest data sets, labeled data sets for that kind of task, with over 200,000 individual labeled light curves so far, probably even more. Some sources do come from CRTS, like projects like CRTS and OGLE, and as one would expect, some classes are more numerous than others. We've been quantizing labels to 0, 0, 25, 0.5, 0.75, and 1 for label smoothing that we're planning to use in the future. And we've been we've been employing an, I would say, active learning like procedure, where we would start off with CTF light curves and external data, cross-match them, produce external features, then pre-process the ZTF light curves themselves, and extract features from them, ingest all that into a fast database, and sample that to build a seed set that is then fed into human expert labeling, out of which comes a training / validation / data set, which we use for training classifiers. Then we evaluate that. The classifications scores are put back into the database, and then essentially we do this loop where we would sample, would select, and inspect random or most confident and or close to decision boundary and or highest loss examples. We label them, we add them to training set, retrain and repeat again. And with that approach, we've been marching down the nomenclature tree. We've been using 2 families of classifiers, deep nets, kind of hybrid, using both dense networks or MLPs for the features part, and convnets for the DMDTs, and also XGBoost. In both cases, using hyperparameter tuning to find the best performing architectures. This is just a slide that I like to show on how the different classes group together in the training set. So that's a t-SNE representation of variable versus non-variable, and this is only variable stuff, and out of that 10 classes were selected. Here I'm showing the kind of performance that we're getting. So I said essentially for every object you get a set of dozens of different scores, and you can play around with them. But then we've assembled test data sets on which we test the performance of all the classifiers, and we've been getting figures like that. So say, for example, for flaring stars, you see that they are variable, but they're not periodic, and they're flaring and not all other stuff. And then with these diagrams, you can immediately see in which cases our classifiers don't perform that well. And that in many cases just has to do with the fact that we don't have too many examples for some of the classes. So stay tuned for the full data set where we're going to switch to that once the pilot project is finalized and published. The results are published. Switching gears again, another project that I would like to highlight here is called SN1A Score. And the intent here is to automatically classify the spectra taken with the SED machine, so the main workhorse that sits on the P60 telescope, the same mountain. And essentially it looks at the spectrum taken with SEDM and tells you whether it's a SN1A or not, and also tells you what its redshift is. And it yields exceptional performance, and with some reasonable score cutout, you send the false negative rate drops below half a percent, and this will allow automatic classification and uploads to the TNS without any delay in CTF phase 2. This work has been led by Christopher Fremling and Yashish Sharma. Coming back to the very beginning of my talk, this is what the data processing flow has been as of ZTF phase 1. And you can see the right side is kind of clunky. There's a whole bunch of stuff. And what I'd like to use the remainder of my time to feature a project that we've been working on since this February. So what we've done is essentially, well, we've decided to condense all these little pieces into a single system that we call Fritz. And the vision behind Fritz is to use it as the main science data platform for ZTF phase 2. And this is essentially an all you can eat, like everything in one box kind of product. It features a multi-survey data archive and alert broker. It features a marshal for all science cases that we have: the transient, the variable, the solar system. This Fritz would be the workhorse for the ML applications and active learning to deliver classification and labeling at scale, and could also be used, and it is also used as a follow-up observation manager, or TOM, as some would call it. Just wanted to highlight the wonderful people that I've been working with. These are the core. These people are the core dev team of Fritz. So it's a joint Caltech/UC Berkeley initiative, but people from other places have contributed as well. This is essentially the schematic overview of how I understand Fritz. So the task is to observe stuff, mine the data sets, discover interesting things, study and characterize them, and then publish them in Nature and other wonderful journals. Fritz, what it does, it combines together two major software pieces called Kowalski and SkyPortal. The first one is the takes care of the data archive and brokering stuff, and SkyPortal serves as the rest of the needs. I unfortunately don't have too much time to talk about Fritz in more detail, but I can do that. I mean, I can spend hours talking about it. So let me just name some of the features that it has to offer. So it's fully open source, as I should say, essentially everything that we've been producing. Once published and accepted, we open source the code and share the models that we build, and where possible, the data sets as well. It gives you powerful alert stream enhancement and filtering capabilities. It features extendable and scalable design. It's an API first system. All interactions can be are performed using APIs. Fine-grained access control. Yes.
You have 1 minute left.
Okay, thank you. So let me just leave you with this slide and show you some screenshots of how it looks in the wild at the moment. So thank you very much.
All right, let's play the applause here. And then open the floor to questions. We have one question in the Q&A from Harold. Do you have unlabeled light curves? If so, what fraction is that?
I'm sorry, could you repeat that?
It says, do you have unlabeled light curves? If so, what fraction is that?
Oh yeah, that's the vast majority of them. So like well over 95%, I would say, are unlabeled. Even given that we labeled like 200,000 light curves by hand. But we do have a tag for each and every light curve at this point. It's just that we haven't looked at all of them with our eyes.
Right. My question is how specific is your how specific to ZTF is machine learning for your method of finding comets? Like I have a giant pile of megacam data, which is a different telescope and a different instrument and all that sort of thing. Can I sort of drop in a bunch of megacam data and find comets with it, or?
This is the hope. So even though it has been trained only on ZTF data, but I don't really see why it would not work for other telescopes. You do need to do some transfer learning for sure. And once released, we'll showcase how to do that with the data of other surveys. So that's really the hope, so that everyone can use that piece of software and look for comets. And we've seen that with other systems that we've put out, that other people took them, did a little bit of transfer learning, and got really good results.
And so
yeah, feel free to contact me. It could be a nice showcase.
Yeah. And same with the streak detector for the fast moving objects and so on. That also.
Yeah, the same. Yeah, the same.
Cool.
Trained on ZTF data only, but in principle can be applied to anything with a little bit of transfer learning.
I assume the LSST people are talking to the Vera Rubin people are talking to you extensively, since you. I mean, I had the same.
To some extent, yes.
So I mean, you've sort of done everything that they're planning to do. I mean, slightly smaller data set, but not a lot smaller, really. And it all seems to be working quite well. So there, to some extent, or.
Yes, I'm not directly involved with the LSST, but definitely we've been talking over the years, and this is also one of the bigger intents to help the community prepare for what's to come. So essentially, all of that can be taken off the shelf and applied to the LSST data, with again a little bit of transfer learning, but the hope is to make it as easy as possible.
All right. Oh, okay. Rob Seaman asks, the major NEO surveys do not rely on streak detection for most discoveries. Rather, moving object detection results from various tracklet techniques. To what extent does ZTF depend on correlating multiple detections, whether for moving objects or otherwise? That is, depend on correlations for discovery itself, not characterization.
So there are actually multiple pipelines that are involved in the discovery of near-Earth objects, and one of them is exactly what you're talking about. So it looks for point source-like detections, and it combines them into sets, tracklets, then does orbit fitting and all the traditional stuff. And streaks are specifically for things that are not picked up by that pipeline because they move too fast and they streak. So yeah, my answer would be there are all sorts of pipelines that do both things, and we're just trying to optimize for for the particular use case. So whatever works best in a given case, we do.
Okay, I'm looking at the Discord and I'm looking at the Q&A and I'm not seeing any further questions. So let's thank Dimitri for his excellent talk, and that takes us to exactly the bottom of the hour.
Thank you so much. Thank you very much.
We're going to have a short break. People can get coffee or wine, or other alcohol, depending on their time zone, or both together. We're not here to judge. And we'll meet again in 15 minutes. Thank you.
All right, Kiri, do you want to try sharing?
Yes, I can share my screen.
Sorry, who would you like to share?
I'm talking to Kiri. She wants to do a
Okay,
test.
okay.
Yeah, good.
Sure, let me give this a try. And so let's see here.
Let me just, where is Dimitri?
Okay, can you tell me what you're seeing?
Your slides, full screen. Excellent.
Okay, does it look good?
Looks fantastic.
All righty, thank you so much.
Uh,
Good day, everybody. Welcome back. The first of the regular talks of this session is going to be Katarzyna Wadega, I probably mangled that name, I'm sorry, of the University of Warsaw and also the University of Texas, who's going to talk to us about artificial neural networks to detect astronomical transients.
Hello,
Katarzyna, do you
everyone.
want to share your screen?
Yes, I'm going to share my screen. Okay, can you see it?
We can see your screen. It's full. There we go.
Okay, thank you so much. So hello, everyone. I would like to talk about using machine learning algorithm, particularly artificial neural network, to detect astronomical transients. And I was using image data in my analysis. So I was working on this project during my master's studies at University of Texas, Rio Grande Valley. And my thesis also was based on this research. And right now I'm continuing, I'm working on this project during my master thesis at University of Warsaw. So first of all, we have different type of astronomical transients, and I was focusing on transients related to gravitational wave events. These kind of transients can occur with binary neutron star or black hole neutron star merger. And first type of this kind of transients was detected on August 17, 2017 by LIGO. And optical transients, which was called kilonova, was found 11 hours after merger near to center of this galaxy. So this is like part of images that I was working in my project. So our kilonova is present on image on the left, and this is like I'm pointing to right now. So we can see like this kind of objects faints really quickly, and the image was taken 14 days after measured. So kilonova is now observed on the sky. So the main difficulties that we have in detecting kilonova are that the probability region where kilonova might occur is really large. So we have to scan a huge part of the sky. So because of that, the detection method should be really quick. And algorithm should quickly analyze huge amount of data. So because of this reason, the machine learning approach could be really useful in this problem. So here I'm showing this example how the sky localization of GW events looked during previous R1 and R2 LIGO Virgo campaign. So in my method, I was comparing images taken by CTMO. CTMO is like a small observatory that is working at the University of Texas, Rio Grande Valley, where I was doing my research. And I compared this image with image taken by SDSS, and I took this image as a reference. So the goal in the whole project was to detect transients on the CTMO image. And this part of the images were looking basically like this. So the whole idea, so image on the left is from CTMO, and image on the right was downloaded from SDSS survey. And the idea was that CTMO can follow up like LIGO alerts about gravitational waves, and somewhere here might be a kilonova. And our task is to detect this one additional object on the sky. So I was working with 5 pair of images. So here we have some more detailed information about properties of the images. So the first step was to download an image from SDSS, and to do that I use Skyview package from AstroQuery. Later I used the reproject package to align image, because it was important to have exactly the same pixel coordinates in both images. And I use images from data release 9 and in gfilter. So the whole idea, later I'm gonna explain more in detail, was like to compare CTMO image and SDSS image, then apply some network structure. And in the end, it should be a classifier that tells us if the transients was observed or not in the image. So it would be really difficult to do this and applying like the whole images. So I decided to create the smaller data sets with like only one object in one image. So first I run object detection program on CTMO image. And after that, I cut like smaller images with only one source in one image. And I cut exactly the same pixel coordinates from SDSS image. And I'm gonna show, so here's example of what Sextractor program gives me on CTMO image. And I obtain this pair of images. So they're exactly the same objects, but one is taken from CTMO image and one is taken from SDSS image. So I created from 5 pair of images, I created more than 3,000 samples. And I call them that they are non-transient samples. And I gave them label that these are, for example, 1. So then I had to simulate kind of if there would be transients on this image, how this pair of images would be look like in this case. So I decided that if Sextractor program would detect the Killanova or transient, so I would have like on one image, I would have some object detected, and on the other, I would have only background. So I use the same like smaller images from the one image, and from the other, I took on this part of the sky that there was only background, and I called them that these are transient samples. So the next step of my analysis was to create training data set, because as I mentioned here, from the 5 pair of images, I have only 3,000 samples, and this was not enough to train like the whole network. So I use another program to simulate like really similar samples, but they are not from real images, but these are simulation data. So here's only a few examples how this kind of data looked. So I call them that these are simulation non-transient samples and simulated transient samples. So the idea is the same, that here I have one object and here only background. So now I'm going to describe what kind of models I built. So I tested 2 kind of models. One is like simple CNN, and the other one is dense model. So I use mostly dense layers. And output, if both cases is the same. So this is like classifier if on the image was transient or non-transient. And that difference also is in the input images, like in second model, the images were taken like 2 separate images. And CNN model, it was like 1 image, but in 2 channels. And I think that important difference between these 2 models is number of parameters that we have to train. So we can see like CNN has large parameters, and it's also like quicker to train. So I trained both this model using simulation data set. It was 10,000 samples. And after that, I calculate prediction on the real data, would mean that the data that created from real images. And the CNN model predicted correctly in 98% cases, and the dense layer in 97 cases. And what is important here, and I think was mentioned in the presentation before, that the main error is like non-transient classification. And I mean by that the network identified like in some cases that non-transients as a transients. So this is like false positive case.
Sorry, you have 4 minutes left.
Okay. So now I'm gonna show like few errors. It was made by this error. So as I mentioned before, the most error is like in non-transient class. So here I'm gonna show a few examples why this error occurred. So like the first example here, like is the one source is basically too weak, so the network couldn't see like this is an object. In another case, the object is shifted, like there's not in the center of the image, so network also made the mistake here. And the third type of error is that another object is maybe too bright and too big, so the network also made a mistake in this case. And I have another set of errors. In these first two cases, again, the object is shifted. And in the example on the bottom, we have like 2 objects in 1 image, and also network couldn't recognize this example. So as I mentioned before, I'm gonna working on this project more. So there's few parts that I could improve. For example, I could skip this part with the simulation data. So if I had like more data from this observatory of any other, I could train the network using only like real data, not simulated. And this is actually the step that I'm working right now, that I'm trying to train these both networks to detect the real kilonova. And also another idea is like I could build more models, mostly with convolutional layers because they are easier to train. And completely different approach is like I could use like generative adversarial network, but in this case, this kind of networks, they transform one image to another, so it won't be a classifier, but maybe changing one image to be more similar to another, and then we can do, for example, subtraction and detect transients in a different way. So this is end of my presentation. Thank you for your attention.
All right, thank you very much. You're well under time, so we have plenty of time for questions. I do not see any in the Q&A. I'm just going to move over to the talks section. I'm not seeing any there either. Oh, sorry, we have one. What method is used to get the simulated data?
So this was a program that I didn't write, but it was based on the Gaussian distribution, and this was basically the simulation. I had to, maybe I'll show the slide. Like I had to set what's like the amplitude of the source and how big is source, but basically everything is like on the based on the Gaussian distribution.
All right, question that, no, okay. Someone's typing a question. Oh, it's gone away. Okay, here we go. Did you consider GANs to simulate your data? From Matteo Trudeau.
I'm sorry, could you repeat?
Did you consider GANs to simulate your data? I'm not sure what a GAN is.
I don't know either, so I think not.
Oh. Is that you, Katrina, there?
Stephen, you're muted now.
Sorry, my computer was beeping at me, and I thought it was a speaker, so I was basically trying to mute everybody on the thing, but it was my own. Anyhow, sorry. Problems firmly between my keyboard and my chair. So okay, so you mentioned generative adversarial networks, and so the question becomes. Did you consider using generative adversarial networks to simulate your data?
Oh, I'm sorry, because I was on mute. Yes, this would be one of my first approach to maybe not use like the simple CNN, but using GANs. But I didn't have like enough time to work on that. But I will do it like in the future.
And then the next question is, how many transients could appear in one frame?
Actually, in my situation, there was no any transient. But honestly, I'm not sure how many. I think only one, because this field of view that we can take, but because I was focusing on my work on detecting kilonova, So I think there would be only 1 kilonova in one frame, because I think it's not possible to detect more.
Okay, well, okay, thank you. Let's thank our speaker one more time here with the applause button. And then we'll move on to our next speaker, who is Curie Wagstaff, coming to us from JPL at Caltech, who's going to talk to us about machine-assisted discovery through identification and exploration of anomalies in astronomical surveys. Take it away. There we go.
All right, just checking. Can you hear me fine?
We can hear you and see your slides.
Excellent. All right, thanks. It's a pleasure to be here. I will be describing joint work with Eric Huff and Uma Rubber-Pragada at Jet Propulsion Laboratory on how we're using machine learning to help us hunt through extremely large astronomical survey data to find what might be interesting and what should be pulled out. And as a case study, what we'll be focusing on is data collected by the Dark Energy Survey, which surveyed 5,000 square degrees of the southern sky using a 4-meter telescope in Chile. And the result of that observing is a massive catalog of 400 million objects, of which about 310 million are galaxies. And there have been a lot of quality filters applied to ensure that this data is very reliable. But even so, as always happens with real data sets, there are still some artifacts and problems that remain within that very large catalog. Yet there is not really time to individually check every single one. But the problem is within that very large data set, if you have polluted observations, it can have adverse impacts on the science you're trying to do with the catalog. So specifically in this catalog, the observations are made at several different bands. We've got the G, R, I, and Z bands that are the ones we're using, from about 400 nanometers up to about 1 micron. And the goal is, among other things, to be able to infer key parameters that define how our universe operates and how much dark energy and dark matter may be present. And so just as a quick cartoon of what we're doing, or what's being done there, is if you have a bunch of sources in the sky and they're just sort of randomly distributed, you might have a bunch of point sources like on the left here. However, if you see a systematic distortion of the light from those sources where they've been stretched and modified, you might be able to infer that there's some mass, even if you can't observe it, that's affecting the light from those other sources. So very careful measurements of the shape parameters of those galaxies where their light's being transmitted to us can help us infer the presence of dark matter. However, if you've got corrupted data in there and some observations that are not trustworthy, you may incorrectly conclude what those parameters are. So it's very important to have highly precise measurements of the objects in the catalog. So our goal was to be able to hunt through this very large catalog to find and understand what artifacts remain that can both help improve the processing pipeline and thereby yield better estimates of cosmological parameters, but potentially also focus our attention on strange anomalies that are present but are actually real objects and might be new discoveries. Our approach is broken into 3 steps. Begins with anomaly detection, of course, within the large catalog. But then because it's so big, the sheer number of anomalies you find is also overwhelming for manual review. So we use an organization step to group together similar anomalies so that we can address them collectively. And then finally, we use explanation techniques to highlight what about this group of anomalies makes them anomalous. Is it that they're elevated in one particular band in terms of magnitude, or is there something else going on that can help characterize what's the problem that has caused them to be anomalous? So the first step of anomaly detection, there are many, many methods out there for doing anomaly or outlier detection. And key questions for us with this task is, first of all, which methods are scalable? Which ones can actually tackle a data set with millions of objects present? And secondly, which ones identify anomalies that are consistent with what a human would have selected as an anomaly within that data set, so that it can be a good proxy for our decision process. And I've have illustrations here of 3 of them just to give you an idea of the different kinds of approaches we looked at. The first one is the isolation forest on the left, which does not assume any particular model of the data, but simply looks for basically sparsely populated areas of feature space. So if you just have a two-dimensional data set, then what this method does is make a series of random cuts through feature space, illustrated by the red lines. And the outlierness of a given object is how many cuts it takes to isolate that into its own little region, like here. So you can see that if you're buried in the middle of the distribution, it will take many cuts to isolate. However, if you're out here on the fringe, only a few cuts would be sufficient. So you can distinguish between items that are anomalous versus those that are part of the main distribution. The elliptic envelope, conversely, assumes that your data is part of a multi-dimensional Gaussian distribution and forms an envelope around that, and then anything outside of the envelope can be considered an outlier. And then finally, the DMUD method uses a reconstruction error-based approach to model the data in a low-dimensional feature space and then see what information can be reconstructed from that. Specifically, it also tries to emphasize diversity in the outliers it finds. So it finds one example of an anomaly and the next one it finds should be very different to give you a quick traversal through the types of outliers that are present in the data set. The second and third steps are designed to help us sort through the large number of anomalies that are found and then understand what they are and why they've been identified. So the second step, we looked at both k-means clustering and a self-organizing map to group those outliers into coherent groups. And then we conduct a review process to try to understand why they're anomalous. We use this web interface to do so, where first we look at the candidate that's been identified, the object which is considered anomalous. And here you're seeing, this is probably small on your screen, but just get the idea, visualizations in the G, R, I, and Z bands of this object, color composite that brings that together into one image, as well as the modeled properties of the source, which indicate, again, magnitude at each of those 4 bands, but it's trying to isolate just this source and not any surrounding objects. We then have automatically generated explanations that highlight which features are anomalous. And here you're seeing basically a gap here. This corresponds to the fact that the object is really only present at one of those bands, which is definitely questionable. And we also have coincident observations from WISE and GALEX of that same sky position to provide context in case to see what else might have been observed at that part. And then finally, you can make a decision, which this is too small to read, but just it gives you the chance to say, is this actually an interesting object? Is this due to some data problem, or is it due to a modeling problem or other issue? And that allows us to classify the different types of anomalies that have been found. So the key question then is asked is, which of those anomaly detection methods is most suitable for this problem? And we were very fortunate in this particular situation. The DES catalog was, the initial version was released, and then several person years were spent in further quality filtering and removing outliers. So we actually can compare our results of automatic analysis of the first version with the millions of objects that were actually removed by a human in the second version and see, is there high agreement or not with the automated method? And of the different anomaly methods we looked at, we found that the isolation forest had extremely high agreement with human decisions about outliers. Perfect agreement would be this dashed black line, and the isolation forest, it turns out, agreed with human decision-making 96% of the time, which is quite good. So out of a total of 14,000 outliers that were found by the isolation forest, they indeed, 96% of them were also vetted by humans as being things we don't want in the catalog. Of those remaining 4% though, what was going on, right? That translates to 538 objects that the isolation forest said were anomalous, but had not been removed independently by human review. So those were the ones we zoomed in on and carefully reviewed every single one, because 500 objects is reasonable, it's not millions, right? So we found that actually most of them, thank you. Most of them were indeed due to modeling or data errors that were, and those subjects should still be removed from the catalog. They just hadn't been removed by humans yet. 9% were normal objects we do want to keep, and 20% were strange things, but looked like real observations that merited further attention. So what did these look like? When I say modeling error, this is an example of where the source has been incorrectly modeled within the observation. For example, the source should always be at the center of this cutout. Yet here we're seeing a hypothesized modeled source, which is probably just merging two real sources, but it's not real. And there we have other examples of incorrect source isolation. For data errors, we have examples like these where you see a bright streak in only one color. Now these composites are from these different bands, and each band was observed at a different time. And so if we see something in only one color, it means it really was only present during that one time when that band was being observed. And so it's a transient object. We believe these are probably satellite trails that just happened to be passing by when one of the bands was observed. Definitely not the sky object we want to keep. We also have some that appear to be observed in more than one band, but with a shifted location, which means that they were moving between the two bands acquisition. And we believe these are probably just asteroids. They're moving more slowly than the satellites, so they're present in more than one band, but they're also not a sky object we want to keep for this catalog. Of more scientific interest, though, we do see some sources that are bright in one band and only one band, but they are co-located with what appears to be a valid remote galaxy. And so we think that, again, these are temporally limited events, probably supernovae that are happening within a host galaxy. So those are also of interest for their own reasons. And then we have some mysteries, some remaining items we cannot explain away, but do not appear to be due to data problems or modeling problems, such as this object which appears purple in our visualization. This indicates that it has high magnitude in the R and Z bands, but low in the I band. And that's unusual enough that we requested a follow-up observation of this object with the Palomar Observatory. And we're able to obtain a full spectrum for the object, which has a peak here at the oxygen 3 line. And if we match that up with our best model galaxy spectrum, which is shown in black here, we find that it's not a very good match. The best match we have within our model zoo of known galaxy spectra does not model this very well. And our current best guess is that it's a galaxy with an unusually high star formation rate, given the total mass that's present. And so we're still looking into that. So to conclude, this is an approach that allows us to find anomalies in very large catalogs. We've shown this with the dark energy survey, but we see that this can actually be a tool going forward for other large future surveys that are going to likewise have very large catalogs to analyze. And we would love to see this approach performed there as well. So I'll stop there and take any questions you may have.
Thank you very much. That was extremely interesting. We do have some questions in the Q&A. Eugene Mangé asks, some very fast asteroids, NEOs, could be as long as the satellite streaks you marked. How long or short could the streak be and be included?
Great point. So, you know, there might not be a really true conceptual distinction between these two kinds of observation, right? They're both moving objects. And for this purpose, we're not distinguishing between them. We just want to remove all of them as being not galaxies, because that's all we want to retain in the catalog.
So I guess sort of my question is sort of related, which is, so you're throwing away all these interesting NEOs and asteroids, like your next slide had. Oh, we find some asteroids, but they're not very interesting. Like, are you tracking these things? Yeah, exactly. Are you tracking the asteroids as well, or recording them, or just like, yeah, burn in the skies, throw it away?
Yeah, great point, because we've had talks already on people who actually want to specifically find this kind of object, right? So for the dark energy survey, these are, you know, one man's noise is another man's data, right? So this is not relevant. However, I kind of skipped over this at the end, but we do want to publish the catalogs of the things that were found, because other people may get real value out of the moving objects, the NEOs, the supernovae, and the other things that we're not wanting to be part of the galaxy catalog exactly. So excellent question.
All right, Peter Skota asks, have you tried LOF?
Local outlier factor. We, for this evaluation, no, although you could add, probably 5 or 10 more methods here for this evaluation. And since we have it set up now to compare with the human review, that it would be very straightforward. Yeah, great idea.
Gabrielle Bien asks, many more satellite trails from Starlink, question mark.
I'm sorry, say that again.
Are there many more trails from Starlink?
Oh, I don't know. Yeah.
Okay, so Peter has asked a second question, but I don't know if it's just a follow-up from his previous one. Is it similar to elliptic envelopes? I don't know, EL, question mark.
The LOF, is that similar to elliptic envelope? Maybe that's the question. I think. There's definitely a relation there. And again, with any outlier detection, it's really a question of, you have to make some assumption about what's normal. And then so that you can define what is anomalous with respect to that. There's no objective definition of outlier or anomaly. And so are you going to assume a Gaussian distribution is what's normal? Are you going to assume something else? And that will then define what your outliers become.
All right, last question before I move on to the next speaker. I might just have missed this, but was there a comparison down to the different categories of the anomalies between the selection methods? I.e., could some of the methods that didn't match as well as the human filtering perform well with specific kinds of anomalies like data corruption, or was there really not much overlap between the selection sets?
Good point. We don't have fine-grained division of the artifacts, the labeled ones in review. We don't have fine-grained classification of them into these different error types, so we aren't able to say that. For the ones, we could look at just this smaller subset because we've already classified them and see what happens with these different methods though. And I think that would be interesting. Thank you very much.
All right, well, I think we'll end the questions there and thank our speaker with the artificial applause. And then move on to the next talk, which is by Joshua Peak of SDSCI, who will talk to us about the Hubble Image Similarity Project.
Okay, so I'm going to be sharing my screen here and starting this talk. Can you hear me and can you see the main title screen?
This is like Tom of the Who. Can you see me, hear me? Yes, you can.
Okay, very good. Hi, I'm Josh Peak. I'm presenting today on the Hubble Image Similarity Project, which is a lot of work done at Space Telescope Science Institute, largely by myself, but also especially Rick White. And I'm putting ADASS here with non-Roman numerals because I don't understand why we use Roman numerals in a place we care so much about data standards. Okay, moving on. So how do we find data in an archive? That's a generally interesting question to me since I'm the PI of the Mikulski Archive for Space Telescopes here at Space Telescope Science Institute. And usually what we do is we look by camera filter, exposure time, PI, metadata, things we knew about the image before we took the image. One way we've solved this problem of looking for things that we actually took pictures of is making catalogs, just like you heard in this previous talk. The catalogs contain some kind of metadata about the individual objects, magnitude, position, morphology, opticity, Sersic index, etc. But we were trying to answer a harder question. Let's say I have a complex image like the ones that are behind me in my virtual background that have lots of structure in them. How do we find, an image that's similar to a flocculent edge-on galaxy or some kind of shock we're seeing, an interstellar absorption cloud? How are we going to find things like that? So in ADASS 27, I gave a talk about a search by image method using convolutional neural networks. Let me explain how that method works, since maybe you weren't all at that meeting and heard that talk. We basically took an image. In this case, our test image was this Magic Mountain image from HST. We cut it up into little tiny pieces, and we fed it through an existing convolutional neural network that has been trained already on terrestrial images, the famous ImageNet data set in this case. This is ResNet 50. There's lots of networks you can use. And then we get these sort of stubby feature vectors. So as you all know, the interstellar medium is about 10% velvet by mass, and then it's 6.4% stingray. Of course, this isn't true, but it does give you a sense that this network is learning something about what's going on in each of these images. We then take these very stubby feature vectors, none of which have a length close to 1, because none of them are actually detections of velvet or binder or gene or stingray, and we cluster them, in this case using t-SNE, although that's we can change as well. And what we find was a really nice result, which is that if you select one of these points in this t-SNE space and you ask what is near me, well, that point corresponds to that red box there on the left, and you can see it's the edge of a photodissociation region. And we're finding the things that are near it, and these yellow boxes are also edges of photodissociation regions. So that's a good sign that this method is working, and that's what we presented in this paper you can read from ADASS 3 years ago. Since then, we've tried this on 20,000 ADASS previews, and we have sort of a prototype system. I'm just showing you a bit of a view of this internal system where we are, able to look in different pieces of this space and snoop around. But what we ran into in building the system, it works. It seems to be doing kind of what we expect is, how do we measure and optimize this method? Okay, this is a method that's trying to say, I've given you an image, I've selected an image, I want to see what's similar in your database to this image. I want to find similar things. But and yes, it seems to be working at some level, but how well? Which network should we use to do this with? Of choices. What parameters should these networks be trained on? What settings? Maybe there's some totally different method that somebody proposes, and we don't know if it's better. We need to know how well this method works. So what we need is a sample of images with known similarities, so we can test and improve our algorithms. So that's where the Hummel Image Similarity Project comes in. So the idea is to create a large database of similarity information between segments of Hubble images. We're using Hubble here because we're really familiar with it. One could easily do this with lots of different kinds of telescopes. Hubble images have lots of detail, of course, so they're a nice choice. We turn this into a citizen science project. We employed people in the service industry very close to Space Telescope Science Institute here in Baltimore, Maryland, who were impacted by COVID-19. There's a really nice fit here where people need to be able to work from home. And they need a fair wage, and we can provide that because we need their eyes. So the way the system worked, we selected a wide variety of images, and we thought that NGC objects would be a nice thing to choose from, because as you can see from once again behind me in my magical virtual background, there's lots of different kinds of NGC objects, galaxies, nebulae, star clusters, you name it. And then we took cutouts of a reasonable size that had enough detailed information but weren't enormous, and ended up with about 2,100 image cutouts to compare. So this is my virtual background. You can see that there's a really broad range of these kinds of things, from little clustered, just star fields, to the centers of galaxies, to nebulae of various kinds, Bok globules, dust lanes, all sorts of complicated stuff that are very hard to classify in any kind of coherent way, even for professional astronomers. It's going to be, each image will be kind of a mix of different things. So the way we did this is we would basically show the participant a comparison image, and we would ask to say, which images do you see that are similar or most similar to this image? And we did this in 3 stages. So in the first stage, we're just comparing every image to every other image, and just saying, which ones even look vaguely similar. In the second stage, we used the information from the first phase here to say, we're going to take all these different images, we're going to use the ones that are already close pairs, and we're going to find the most similar image. And then the last one was a very high level of refinement, where we're also rotating the images to make sure we're not just being fooled by the orientation of the telescope. So this is what a phase 1 review might look like for one of these citizen science folks. On the left side is the comparison image. We replicated it twice so that it was easier to compare on a screen. And you can see that they're allowed to pick sort of as many ones they think are sort of vaguely similar as possible. And then finally, this is what phase 3 would look like. You've got a comparison image, and it's much harder. You can see all 3 of these images look quite similar in some way. Thanks. This was designed for community impact. As I said, this is trying to employ service industry professionals in Baltimore, waiters, yoga instructors, lots of different people. And we designed it to pay a fair wage. We use the Amazon Mechanical Turk system. I don't know about your institutes, but it's very hard to hire 50 people kind of like that. We started this in March. We were working by April. We were done by August. So there's a really nice article in Wired if you just type Sarah Scholes Wired. And this is a really great article, both about our project, but in general about citizen science projects and astronomy. So you can nice interviews with people who worked on our project, our neighbors. So we did almost 1 million reviews of 5.4 million pairs. That allowed us to build up a similarity distance matrix between all pairs, so a 2100 by 2100 matrix. We can use that to construct groups and to construct dendrograms, and also to try to figure out the closest, pair and basically make a hierarchy of pairs between every single one. There's some fun ways one can work with these data. The idea is to publish all of this publicly so people can use it to train their own networks, to train their own systems, to test their own systems, and just to use in general across machine learning. It's a really interesting data set. And we can use the results to assess the accuracy of algorithms for our search by image functionality that we're going to be moving forward with at MAST. Hopefully I'll present about that someday when it's ready for prime time. And it's also worth, these data are quite rich and they may actually be useful in even some level of lightweight training. Mostly we're thinking about them for testing, but they can be useful for training. I'll just quickly show you here a little notebook we have. I hope you can still see my screen, where this is the result of taking not the network's output, but the output of the users and clustering them. So each one of these points is an image. And if I click over here, what I get is the image that I clicked on is over here, and then all the images that are most similar. So here you're just looking at a pretty boring group where people are saying, yep, these are kind of star fields, maybe with some gradients. As we move over here, we start to see lower density gradients, lower density star fields, then maybe a bright star pops up as we move over to here. So you can see there's a really nice grouping here of continuity. We jump over into this region and you get into the interstellar medium. You can see places that have very bright linear features. You can see places where there are opacities here at the edges of photo dissociation regions. If I jump over here, we're now looking at little star forming regions. Sorry? Star forming regions. I'm almost done. And then as we move over here, you can see that this space is just really fun to explore. But you can see, these folks who really don't have any astronomical background in their work, about 30 people from the community, are doing an incredibly good job at putting similar images together. These are flocculent spirals with really nice thin dust lanes. I mean, I can keep wandering around in this space, but I think you've got the impression of what's going on. As we wander over this way, we start to get to galaxies that are that have cores that are elliptical cores and bulges and so forth. So this is a pretty neat demonstration that what these folks are doing is really useful and that this will really be helpful in testing out our algorithms. So maybe I will stop there and take questions.
Thank you very much, Josh. We have one question in the Discord, which is, great idea to pay a fair wage to people who help, especially in this pandemic. Can you please elaborate on how much that is per hour of work, per number of classifications made? Thanks.
Yeah, we aimed, it's a little hard because Amazon Mechanical Turk is designed by the task. And so we tried to work pretty carefully to get it in the right, to fine tune it. So we got to about $20 an hour, which, in consultation with folks here in the industry, that would seem like a reasonable wage for this work.
Henrique asks, are the people who selected the images eligible for authorship and eventual publications?
That's a great question. I'm going to be reaching out to them as we move forward with this, and I'd love to get their input. I certainly would like to acknowledge those people one way or the other. I'm not sure if that, what's the word? That's the kind of value that they're looking for, but I would be very happy to have these people as co-authors. They're all really great, and it's been a lot of fun working with them. Actually, what I'd like to do is talk to people who've done citizen science work, Chris Lintodd and the world of this universe, and ask them how they've done that and what they've learned from that, because there's a lot of knowledge there that I don't have. So if you have thoughts on that, please reach out.
Mark Taylor asks, how much guidance of the work is get about what counts as similarity, e.g. relation, rate W?
Right. Sorry, I didn't quite catch the whole question, so I'm just going to pop over to Discord to make sure that I can understand it best. But yeah, exactly. So yes, we gave them some instruction. We had a couple of Zoom sessions to begin with.
About what
I'm not sure if it's me or you, but I'll just speak. the answer is we had a few Zoom sessions with them to answer questions, and we were always available. We got a bunch of emails from certain people early on in the process where they said, okay, I see this and this. Did those count? Does that not count? And we, there were moments where like, oh yeah, okay, so you're getting a little confused by orientation or what have you. And so we found that those kinds of conversations were really useful. This is a really good reason why doing this with people and hiring them rather than just saying we're going to pay the lowest possible wage and just get random people from the internet is pretty nice because you get to work with them. I know there's also citizen science projects that are on platforms like the Zooniverse where there's lots of conversation. So we found those kinds of conversations really helpful.
So just going to ask my own question, which is, so Hussein Tomarian at the CDC was working on this, and he basically has come up with the exact same results with you with using self-organizing maps, I believe it was. The question is, like, how do you feed that into the search engine? Like, people who like pictures of globular clusters might also be interested in this other, and that was sort of
I mean, I think what we want is a system where either you say, here's my image, here's my John flocculent galaxy or something, find me things like this. So that kind of thing, or, draw a selection box in an image that's already in the archive and then say, find me things like that. The Amazon, like, oh, I'm Clippy and I want to tell you that you want to find this. I think astronomers know what they want. We have to make it, there's always a culture change question. How do we help people know that this service exists? But I think it's pretty clear that we want to say, bring your own image or select a piece of our image and we'll help you find things that look like it.
Shabir asked in Discord, some of the data points images after feature reduction when clustered are intertwined with each other, like the orange and gray dots. Not sure that the example helped. How are these images differentiated with each other?
Good. So the coloring of the dots comes from a dendrogram analysis, which is to say you have some complex set of, this is like that and this is like that. And then the dendrogram tries to say, we put them into groups. And we know that that's not necessarily reasonable, right? You can have an image that has, I don't know, some nebulosity, but also has an ellipsoid. And so it's going to be like ellipsoids and like nebulosities. And so the idea that it's in a group is sort of ill-posed. So this coloration is just coming from that. It's just, the way the dendrogram works. I don't think we need to use the dendrogram analysis because we're not actually trying to cluster the data. We're just trying to say, A is like B and B is like C and C is like D. So if you give me some new image, I'll just tell you the ones that are most similar to it. We don't have to do clustering because I don't actually need to be told that there's a group of thing called galaxies and a group of thing called, molecular clouds. I already knew that.
The last question is, do you have examples of scientific application of the search by image similarity feature?
Sure. At least for me, as somebody who studies the interstellar medium, I'm really interested in scalloping in shocks. And I know of one cloud that has this kind of scalloping, but man, it sure would be nice to know that, if I was going to go point some big fancy telescope at all the scalloped shocks that exist, I'd like to know that I'm looking at a big chunk of them, or at least to find some new ones. So to me, these kinds of tools are really helpful for trying to do follow-up analysis, where you're trying to say, look, I want to have at least 3, 4, 5 examples of this kind of thing that I'm after that has some kind of structure to it. So to me, that's a really interesting use case. I think it'll become even more powerful as we expand. We have higher and higher resolution images, especially from space, across larger and larger areas of sky. So think Euclid, think Roman.
All right, well, I think that's all we have time for. In fact, we've gone a bit over, so let's thank our speaker by mechanical applause again. And the next session is a bunch of lightning talks, which are going to be run by Alice Allen. So take it away.
Oh, there she is, I guess.
Yes, that's right. So we have four lightning talks, and the first one is by Susanna, who I hope has raised her hand and has been given permission to speak.
Hello, can you hear me?
Okay, good.
Okay.
Okay, and she has 2 minutes.
Can I start?
Yes, you can start.
So my name is Susanna. I think many of you know about the SKA, a project to build the largest radio interferometer with thousands of antennas in Australia and Africa. This instrument will be able to produce around 600 petabytes of data products per year and deliver this data to a network of SKB regional centers. And in these centers, it will be where the astronomers analyze scientifically this data. So the SKB regional center will be the core of the SKB analysis of the SKB science. And for this reason, we think that we need to pay us in the Instituto de Astrofísica de Andalucía in Spain. We think that we need to pay a special attention to scientific reproducibility and open science. So in particular, we are developing a SRC prototype, leveraging the flexibility of the cloud computing that allow us to incorporate services and tools as long as we are identifying tools and services that are able to support open science and scientific reproducibility. One of these tools is a science gateway. In particular, we are members of the European project ESCAPE, and we are contributing to develop a science platform for accessing data and tools of the astronomy and particle physics community. We are also identifying best practices to enable scientific reproducibility from 2 points of view. From the point of view of the astronomer who wants to reproduce and automatize their analysis from the beginning to the generation of the tables and plot of the paper, and also from the point of view of the SRC, of the SKB regional centers, or other science platforms in astronomy, which wants to provide the framework and the tools that are able to support open science. We have other activities. For example, we are analyzing how we can use provenance in order to support open science. We are also contributing to other working groups interested in science archive, like Wallaby, and also contributing in the team interested in radio inside of the...
Thank you.
Okay, thanks.
Thank you.
Sorry, I didn't see the timer.
Hi, do you hear me?
Yes.
Okay. Hi.
No.
New issue region catalog from the Califa survey and the software that we use to generate it. This catalog comprises information from around 26,000 individual regions, including the flux intensity and equivalent width of 51 emission lines in the optical spectral range and the properties of underlying stellar population. We use the semi-automatic script PyH2 Explorer for the extraction and subtraction of H2 regions. So we know that the H2 region are structured with strong emission lines that are clearly above the continuum emission. Therefore, we developed PH2 Explorer to identify clumpy structure with a high emission from an emission line map, for example, from a H-alpha emission map. To identify clumpy structure from an emission map, PyH2 Explorer needs several parameters to define clumpy structure, like a minimum flux limit to identify a peak emission pixel. Also, some input parameters determine the relationship between the peak emission pixel and the other pixel that define a clumpy structure, like the distance to the peak emission the peak emission pixel. So the output of PyH2 Explorer is a segmentation map where each clumpy structure have a unique ID, and the complementary map where all clumpy structure are masked is provided as well. PyH2 Explorer has been tested on Califa and Manga data, and currently a new version for high spatial resolution data like Muse is under development. And if you are interested in PyH2 Explorer or the H2 region catalog, you found the link to the corresponding website in my poster, or send me a message in Discord. So that's it. Thank you.
Okay, you've got 20 more seconds if you'd like to say anything else.
Okay. Well, the last figure in my poster is the BPT diagram for this H2 region. So with this sample, we define a new demarcation line for the BPT diagrams. So that is very interesting too, because we define we identify the clumpy structure with the definition of H2 region. So look my poster, actually, for more information.
Thank you.
Thank you.
Somebody's hand is raised, I hope.
Yeah.
Thank you.
Am I audible?
Yes.
Okay, thank you. Hi, everyone. I'm Athanasius Ramaila from the South African Radio Astronomy Observatory. So at Sarao, we work on this project called CAN. So CAN is a set of astronomical packages or softwares that are released for Ubuntu operating systems. Currently, we have CAN 6 available, and the upcoming CAN is CAN 7. So basically, this is to alleviate the problem that many astronomers are facing in terms of software installation. So we package these softwares and publish them as Debian packages, and astronomers can easily install them. So that most of the time isn't focused on this software setup or pipeline setups, so that most of the time should be focused on doing real science. So this set of software tools are available also in containers for users who are not using Ubuntu system, so they can easily access them through the containers. And also, if you want to interact with us, you can go through the GitHub page. You can open an issue there, and then that will enable you to communicate with us. You can ask questions, and as well, you can contribute. So not to say much, but if you're interested in this open source packages, feel free to contact me or drop me an email or visit the website of CAN.
Thank you.
Yeah.
Yeah, you've got 10 more seconds if you want to say anything else.
10 more seconds. I can just wish myself a happy birthday.
Happy birthday.
Thank you.
All right. And then last but not least is Rosa. And let me find out what happened to hers, but go ahead and start and I will figure out what's going on here.
Okay, so I have a poster talking about improvements in our practices to support the development of astronomical software at STSCI. And as you know, as STSCI, we support several missions. So we have been able to leverage our experience managing and supporting the development of the calibration pipeline for HST to improve on JWST processes and enhance the collaboration between developers and scientists that work in this mission. So in this in the poster, I show how we work with Hubble and the limitations that it has, meaning that HST has a pipeline for each of the instruments, and therefore the groups work independently. And I'll also show how this contrasts with the way that we work in JWST. The development teams and the scientists were able to come up with a combined single pipeline for all the JWST instruments, and also added the benefit from adopting a programming language that was familiar for the astronomical community, which has enhanced the collaboration between these two teams. And also, in particular, I focus about the importance for us to establish and define a process that keeps this level of collaboration going through the whole process of the project, and also a process that works for both groups and take into account the divergent responsibilities and priorities that these two groups might have that can break at any stage of the project. Finally, I list the most relevant steps that we have taken to make this more successful. That is regular communication regarding the changing of priorities between these two groups, also defining clear roles and responsibilities for the decision making and the prioritization of the work, even for the scientists collaborating in the project, and also adopting project management processes and tools across the science team and also the developer teams to communicate and manage work. And by implementing these few steps, we have already seen more collaboration and improved relationship between the scientists and engineers, and with this, the overall success of these projects. So I think it is very important to keep the collaboration going, to keep it growing improving in these processes as we work in more projects at STSCI. So thank you.
Great, thank you. And that's it. Let's please thank our speakers, yay, for their lightning talks. And then we are leaving you 15 minutes to go do whatever you need to do in 15 minutes, right? Thank you.
Hey, Alice, with all this thing of trying to get the poster together at the same time that I was going to talk, I don't know if I forgot to put the microphone in front of me. So I hope that everybody was able to hear.
Oh yeah, no, the sound was great.
That was good.
Yeah,
good.
The sound was excellent. So I wanted to explain to Kathleen, I was just starting to do that, why I had two machines going. The machine that I'm using to present the posters is one that I prefer, but it overheats when it's running Discord and Zoom and all of that. I actually have it sitting on a bag of frozen vegetables to keep it cool long enough to get through this. So I'll go back to using the other one.
I assume it was something like this. It was very confusing figuring out, because they have exactly the same name, the two accounts. So which one's which?
Yeah, it's and I'm sorry for the confusion. Yeah, because I'm logged into Zoom or whatever with the same name, but so I've been watching Zoom on a Chromebook, but I can't do, like, I could not have presented these posters this way on that easily. It was just so much simpler because I was doing it very quickly on the fly, just simpler to use this machine, which I'll now
Can I share the screen? Do a test?
Yes, please.
Somebody's already sharing. Thank you.
Nope.
Share the screen.
I got my microphone today, by the way. I ordered it yesterday.
Oh, the same one as mine?
Same as yours. I'm not using it right now, but I ordered it yesterday with the free shipping.
Voila, there it is. Can you see it?
Now we can, yeah.
Yeah, okay.
Hey, Peter, you put me on the microphone business too. I just got one.
Oh my God, who is that?
What? You got one too? I need to be compensated for this.
Can you stop sharing, Peter? Because I want to offer other people.
Like Alice, my machine is so hot and slow.
Well, that's why I've got frozen vegetables underneath it.
Oh my God.
I mean, literally, it's on a package of frozen vegetables.
Well, there is a stop share.
Bill, do you want to try sharing?
Can you steal it away from me?
Steal what away
functional. This is not good.
I can stop your video.
Oh, co-host has stopped your video. But he's still there. Oh, this is not good.
Oh, okay, I'm back. Goodbye.
Okay. I guess I'm ready to try sharing video too.
Okay.
Just a second. Let me pop it up here. It's on my screen. Let's try share screen. Share screen. And hit the button. There, share. Okay, screen 2. Share. It says it started. Okay.
That's good.
And there I am. I
Yep.
put on a second Zoom just so I can see what's actually appearing. So,
Okay.
so that's why I'm in the
Well,
system
let's,
twice.
Bruce unmuted himself, so maybe you want to try as well, Bruce?
Yes, please.
Okay, I'm stopping sharing.
Okay.
There you go.
Thank you.
Mine is a total disaster. It still claims that I'm sharing, but obviously not.
No.
Okay.
Now Bruce is sharing.
That's good, Bruce.
Thank
Thank you.
I will.
Sorry, we checked. I was AFK for a few minutes there. Did we check William's?
No, everybody was talking. I was trying to get Bill's attention. Bill Pence, if you're here, do you want to try sharing? Might have gone for coffee.
No, he's there.
Oh, there.
He's muted. Oh, there
All right. Can you hear me?
Yes.
We can hear you.
Okay. I do not have any slides to show, so all I need is my camera.
And it works beautifully.
Right.
We hear you and we see you.
Great.
Excellent. Thank you.
Wow. This is going to be fun. I will.
Katerina, did you want to give it a shot?
I'm going to stop video.
And Jan is going to join us later once the kid is in bed.
Ah, okay. This happens.
Yes. And Oleg, you're on in this next block. Do you want to do a share screen test, or are you good to go?
Yeah, I'm good to go. It seems.
Okay, Sana.
Is it sharing?
That's sharing.
Yep. So this is weird. I don't get the gallery view on my laptop. It won't give me one. Ah. That's very strange.
Peter, I have a microphone. It's not like yours, but I think it is good too. I don't know if you know the blue. You see this microphone? I cannot hear you. You are muted.
The embarrassing sentence. Yes. I realized, I don't know how yours is, these things can collect dust. So I think since I won't be using it a lot, I think it should be covered when you're not using it, because it would be bad if the dust would accumulate inside.
I don't know. I have had it for a long time and I don't know.
Yeah, mine doesn't have a soft cover. It's a wire mesh. So
mine too. Yes, it's a wire mesh. So.
I probably should put a little plastic bag over it to protect.
That's a good point.
So who saw me eating spaghetti this morning?
Me.
Oh my God. I looked at the YouTube and I didn't see it in there.
Oh,
I thought that that was a pointer for the speakers to stop talking when you're eating spaghetti.
Oops.
But then I realized it was not.
That's right. Okay.
Can I maybe just try and share my screen, or is it too late?
No, I think you do it. Yes, you can do it.
Okay.
There it came.
That works perfect.
Yeah, perfect.
Too easy. Thanks.
So who here remembers, the Who? Tommy from the Who.
Yeah.
Which is, can you hear me? Can you see me?
Yeah. That's classic us. That was the first music cassette I ever bought. Because I didn't have a turntable in my dorm room my first part of my freshman year, but I had a tape recorder. I had a really great Philips, an original Philips cassette recorder that I got from my graduation.
They were good. Philips made really good cassette recorders.
Funny, it was rebranded by 3M, but it was the same exact mechanism and everything. It looked like the Philips.
Oh, welcome, Bill. I hadn't seen you yet.
Yeah, he's there. Everybody moves around on the screen, so you never know. As soon as someone new comes in, everybody shifts or gets shifted.
Bill, do they still allow you at NASA Goddard? Do they still allow you in?
Basically, nobody's allowed in unless you're doing critical work. So maybe 5% of the staff goes in. I can't even go in to play tennis, so yeah.
What about the farmer's market? I guess that's stopped too.
Yes, that's certainly gone.
We've had our local farmers market has been going on through everything. You have to go in masked and get your hands get your hands sanitized as you go through the entrance, and they only allow a certain number of people in at a time.
Our department is still organizing their Christmas party though, so it'll all be virtual.
We had an Oktoberfest a couple of weeks ago, all on Zoom. We had our summer barbecue was on Zoom too, with no food, which was sort of disappointing.
We did Oktoberfest, but everybody has to make their own schnitzel or sausages or whatever.
Yeah.
And the dancing doesn't work quite as well by a Zoom.
No.
Hi, Bill. It's Alice. I just wanted to congratulate you on your software prize. I was so pleased to hear about it.
Yes, well, I'm very honored and surprised too. So thank you.
I wasn't surprised, but I'm really happy that you got it.
There was some good competition.
There was competition. That's true.
I have to.
Certainly.
I don't think we need to run a competition like a request for proposals, because like all of them were in the top within half a point of each other when we put at the end. Rob Siemens in the Q&A says, "Congratulations, Bill." But we're sort of jumping the gun here. We got three more minutes.
Yeah, we're up to 100. Now that it's over, I've got to go back and view all the videos of the things I didn't see because they were in the middle of the night.
Well, 100 here, but there's also YouTube.
That's true.
Yes, exactly.
There's typically 1/3 of them on YouTube, 1/3 to a half or so. Bill, were you able to peek into some other things that we did this week?
Yes, I tried. I have to say most of the talks were over my head, and things have changed in the years I have not been actively in the group. So many more things are in the cloud and off the. Back in my day, it was more what can you download and put on your Linux box and do good things with. But it's very interesting, and I'm glad to see the meeting is certainly thriving.
Yeah, this was one of the more interesting ones of recent time, actually. I think a big diversity of issues and things moving to the cloud. And it used to be data in the cloud, and now it's computation in the cloud.
Right.
Also spend lots of money on the cloud.
Yes.
I like that word, a fiscal black hole.
Yeah, I mean, it's tricky because it means a bunch of local people aren't getting employed and a bunch of people at really big tech firms are getting employed, which I don't really like.
Oh yeah, we always have to tell people now, of course, even in virtual way, please turn off your cell phones.
And if you're at home, you have to have people turn off their devices, their audio prompted devices.
Oh yes.
So we're at the top of the hour. So welcome back, everybody. I trust everybody's got a beverage or coffee or what have you that they need. We're going to start off this next batch of things with the brand new ADASS Software Prize. So this year, the ADASS Program Organizing Committee has instituted a new software prize. The prize will be awarded every year at ADASS for an outstanding contribution to astronomical software. And the winner of this year's prize is William Pence for his work on CFITS.io. CFITS.io is a library of subroutines, which doesn't really need an introduction, but anyway, here we are, for reading and writing FITS files, which have been using countless astronomical software packages over 2 decades. Provides a de facto reference implementation of the FITS standard in addition to supporting common extensions used by the astronomical community. CFITS.io has proven to be robust, portable, providing a stable code base for numerous projects across many operating systems and development languages. This award is presented in recognition of the outstanding contribution of CFITS.io to the astronomical software community for Bill's efforts in leading projects since inception. On a personal note, I'd just like to say I use FITS.io every day, sometimes millions of times a day. It always works fast, and if it doesn't work, it's because something's wrong with the data. So I am now going to hand Bill the actual physical prize here by running up the screen. And then Bill, you can...
It's coming, here it is. That's tight fit through the USB port.
And so I'm just going to play the applause track because unfortunately everybody's still muted. But Bill, if you would like to say a few words about FITS.io, take it away.
All right, well, thank you very much. I'm very pleased to be here. I just wanted to show everybody this neat prize, which is a recycled computer hard disk drive. And the platter has been engraved with the words ADASS Software Prize 2020. And it's certainly a fitting prize for this award because my software was really geared to accessing files on devices just like this. The only problem I have is I'm not sure how many gigabytes I can store on this thing yet. But seriously, I'm truly honored and grateful to receive this first award for the ADASS Software Prize. It's especially meaningful to me because it comes from my own peers in the software development community, many of whom I've known and worked with for over 40 years. I would have to say, in all honesty, that I think this award to CFITS.io is actually a very inspired choice by the ADASS because the ADASS meetings and participants are directly responsible for many of the innovative features in the software that have made it so useful. I had the pleasure to attend the first 23 ADASS meetings from 1991 to 2013. And those years coincided with the time that I was actively developing CFITS.io. So at every meeting, I would come and talk to people about progress, issues I was having, and I would always return home with several pages of notes about ideas and suggestions, as well as a few complaints about CFITS.io. But more than that, these meetings led to active collaborations with many people who contributed their own time to write and donate actual working code that is now distribute as part of the package. So I wanted to take this opportunity to briefly outline the history of CFITS.io and highlight just a few of the major contributions that others have made. Then I'll end with a few lessons learned and what I think I've learned about producing successful software. Just briefly, for those of you who are not familiar with CFITS.io, it's basically a library of subroutines that allow C and Fortran application programmers to read and write FITS files, and it hides most of the internal complexity from the user. But it's really much more than that. It has very complex internal computation functions which allow you to which can be invoked at high levels without having to write much C or Fortran code at all. I guess if I was asked what is the main benefit of CFITS.io, it has been to make FITS files more accessible to the average programmer. Back when I wrote it, few people knew how to write FITS files. A FITS image and a few keywords was not difficult to create, but FITS binary tables were a whole nother kettle of fish, as we would say. CFITS.io made it possible for almost anyone to write FITS files rather quickly. And maybe one of the benefits to that was it made programmers less likely, less inclined to invent their own binary format or to do something different. And it may have helped solidify FITS as the standard format used in astronomy. It's hard to believe that the origin of CFITS.io goes back 34 years to 1986, when I bought a DEC Rainbow microcomputer, which was a rival to the IBM PC. It came with a Fortran compiler, and I could run the same data analysis programs at home as I would run on the VAX machines at the Space Telescope Institute. And I would transfer data back and forth on these massive 5-inch floppy disks. And so to read and write the data files on each machine, I wrote a small library of data access routines. And I didn't know anything about FITS at the time, but designing that data I/O library provided valuable experience when it did come to writing it in a few years. In 1990, I joined a new project called the HEOSARC at the Goddard Space Flight Center, NASA. The HEOSARC had two main mission goals. One was to build a public data archive for the data from NASA's X-ray and gamma ray space missions. And it was already clear then that we would archive the data in FITS format. And the second main mission was, for the HEOSARC, was to develop a software data analysis system for calibrating and analyzing those FITS files. We considered adopting one of the existing widely used systems, such as IRAF or STS-DASS or MIDAS. But one of the drawbacks to all of them was you needed to first import FITS file into the proprietary internal format that analysis system would use. And likewise, any data products you made would have to be exported back to FITS format before being distributed. So after more discussion and debate, the HEOSARC decided to make its own new data analysis system, which used FITS as the working data analysis format. And this had the advantage that our software, which we called FTools, which stands for FITS Tools, it could directly read the FITS data in the archive via FTP or HTTP access, and it eliminated that import and exporting step. So in a nutshell, that's how I ended up being volunteered to write the data access library, which I wrote in Fortran, and that was used by the HEOSARC for all of its analysis packages. This initial version didn't take that long to write, and it was quite basic and nothing very revolutionary about it. and it certainly was not prize-worthy at that point. I'll just mention one other significant event in the development history, and that occurred in December 1995, when the US government shut down for 3 weeks because the politicians couldn't agree on a budget. NASA and HEOSARC were shut down, so I suddenly had a lot of spare time on my hands. So I decided to teach myself how to program in C and started writing the C language version of the FITS library. That turned out to be quite fortuitous because many of the enhancements that were made later were much easier to implement in C rather than Fortran. So as I've mentioned, over the years, I've received literally hundreds of suggestions for improving the library. Many were a direct result of the contacts I made at the ADASS meetings. I'll just mention a few of them here with apologies of ones I've had to leave out. And in all these cases, pardon?
4 minutes.
Okay. So in all these cases, I probably wouldn't have thought of doing it myself, and it would have been maybe beyond my capability in any case. So I'll just mention it here. One is some lexical parsing algorithms that do on-the-fly filtering of FITS tables. This precompiles the expression in a way that can be rapidly evaluated. Another one is the CFITS.io iterator function, which can rapidly stream through a table and select rows that are of interest. And so I highly recommend that if you are doing computationally intensive operations on large tables. And just the last one I'll mention is one of the biggest, which was the image and table compression methods that were developed in collaboration with Rick White, Rob Seaman, and Doug Tody. And these have now been incorporated into the FITS standard itself. For other contributions, I'll refer you to the acknowledgement section of the CFITS.io User's Guide, and it lists more than 80 people. Just in the remaining couple minutes, I'll just randomly throw out a few things I've learned over the years that makes good software. One is that truly new and innovative software usually comes from an individual, or at most a small group, who are thinking outside the box. They don't come usually from big projects with formal design and review process. So this means I think programmers should always be allowed to have time to pursue some interesting new idea, even if it doesn't seem like it's immediately relevant to the project at hand. Another thing I've learned from experience is worry about the corner cases. If it works 99% of the time, you still need to fix that other 1%, because somebody's always going to wander in that corner, and it's harder to fix later than if you do it right now. Software distribution must be easy and painless for users. Ideally, it should be free and not require any registration or a lot of contact information. And the software should come with a standard software license with few restrictions. Unfortunately, CFITS.io is not a very good example of this because the NASA lawyers insisted on drafting unique wording for the CFITS.io license. Finally, in closing, I'll just thank the people again, and I think this software award and others like it are really important and are an excellent way to recognize and promote the careers of software developers. Scientists can rely on their publication record as a means of winning job promotions. Programmers don't have this course, so awards like this can be very significant for their career advancement. And I'll note that this is especially important for the younger or mid-level individuals. So I certainly hope the ADASS will continue awarding this prize in future years. And I'd also suggest that more organizations and institutions should consider establishing a similar sort of software award to to recognize outstanding software achievements within their ranks. So thank you very much.
Well, thank you very much, Bill. That was excellent. And thank you for CFITS.io in general. I'm looking at we don't have a lot of time for questions, but I'm just looking at the, looks like there aren't, oh, okay. Okay. One question. I was curious to see what the reasons might be for the naming, writes Paul Barrett. I guess it's just FITS.io.
Originally, it was FITS.io. It was written in Fortran, and it was pretty obvious, FITS.io library. And when I wrote the C version, I had to distinguish it from the original, so I just put the C on the front. And eventually, the Fortran version was retired, and now there are wrappers on top of the C programs that Fortran programmers could call.
And then one, sorry, advice for current data formats debates?
FITS is not perfect, I certainly know that, but the fact that it is such a common data language among the community, I think is very important. And it would be hard to replicate with any new format.
And then regarding, Thomas writes, regarding CFITS.io, what is your biggest regret?
That I didn't make a dime off of it. Actually, I was thinking I should put in a little time bomb, so in a few years it'll encrypt all the FITS files, and I'll fund my retirement by requiring you send Bitcoin to a certain address. But realistically, I don't know, it's just been a fun thing, and I think it certainly couldn't be planned, and so it's just, it formed the basis of my career, actually.
Well, thank you very much, Bill. It's been a pleasure hearing about this, and again, yes, thank you.
Sure.
We're now, so the next stage of the day is the BOF of BOFs. We're going to hear from all the BOF organizers who are going to report back on, give synopses of all the birds of a feather things that have been going on. So who's managing that, or is that my job? Who's going to be the first person?
It's supposed to be assigned to Francesca.
Sure, I can do that, but I mean, Stephen, if you want to do it, I was just thinking of going, in chronological order, starting from Monday, and skipping over the people who are not online yet, and then fetching them back up later. But I see, for instance, Jan, he's online. He was in many BOFs, and definitely was organizing the first BOF of ADASS 2020. I'll get a little bit higher. And so Jan?
Who's presenting for, if we're going in order, who's presenting for best licensing practices?
That would be
Jan,
me.
I would.
Yeah, all right.
The guy who was in half the BOFs. But I'm preempting only one, okay? So you'll get, you won't see as much of me as you did for the rest of the BOFings. Is this my screen?
Yeah.
Okay, so, well, just to tell you, it's a summary of my BOF. I actually presented the same slides in the third BOF as well. So just a list of the fantastic team that we did it with, I think. Whoops. So the summary, well, I think we were all very surprised by the huge attendance of this meeting. More than 120 people interested in this topic is just amazing. We found out that it's widely accepted. I mean, we found out it's clear that it's widely accepted that source code licenses are a must, right? You must license your code. the main issue is indeed is not that whether or not to choose a license, but what license to pick. And I mean, there is a lot of complex discussion because of external constraints as well, and things like that. Permissive license tend to be more used than non-permissive ones. I think that one of the things that I found out by doing some quick hacking with the data that we got out of the questionnaire is also that even from the people who do not, who decide not to follow the policy of their institute, that is in most cases because they want to use a more permissive license than their institute wants them to use. So I thought that sort of says something about their community, I think. Well, relicensing was a huge topic, I think. And there's a clear wish from the community to share these things and learn from each other. I didn't even change the typo after Monday, I see. And exchange guidelines. So just to show you the nice 2 graphs from our questionnaire, and of course the URL that you all can visit for documentation. So that's here. I'll let you parse the data. I think that there is certainly a lot of potential for follow-up discussion. So I would probably say see you next year in some way. Data licensing is an interesting topic. Contributions are an interesting topic. How do we enforce licenses at all? And again, the collaboration on a community-based approach is something that I think came out of this. That is something we should think about in some way. That's it from me.
Awesome, fantastic, Jan. The next BOF that we have on the schedule was still on Monday. We have 3 BOFs in total on Monday, and it's interoperability of users, developers, and managers. And that was Jan.
I think Jan may not be online. Either Jan or me can do it. I have a slide here. I don't know what Jan's status is. He may also have kid duty. I don't know what happened. Is he still there, or should I do it? I guess I should do it. Let me share the screen. As spotlight. It's a little slow. Yeah, there it is. Share screen 1. Put the slide here. I'm going to do it this way because I had problems unsharing. So this was the interoperability between users, developers, and managers, the 3 stakeholders in what we used to call the gaming table. Long time ago, ADASS was using these. I was part of that too, a long time ago. The FATS tradition. We had 3 or 4 of them. So we had a very lively discussion. We picked it up last year again, if you may recall. There's a nice write-up of that in the proceedings. And we decided to continue that on. As I said, there was a lot of discussion. We now, as Jan likes to say, we have a treasure trove of comments and names. We did a few polls. This will be summarized in the paper. And we will clearly follow up with the people that made good comments online, because it was quite challenging, as many people have also said, to keep track of the Q&A and the Discord and the spoken word. So look out for the paper, and we clearly have an idea to continue this tradition and try it again next year in Cape Town. Okay, so that's one. I'm going to slide this out because I happen to be the next one as well.
That's right.
Yep, there it is. I'm not going to do full screen because I'm afraid of being not able to unshare. So the third BOF, the last BOF of Monday, was about the topic how to better describe software for citation and discovery, done by myself, by Alice Allen and Bruce Berryman. And for those who know the ASCL, will recognize that all 3 people are involved in the ASCL, and that was the origin of this discussion. So what do we mean by that? We wanted to discuss the issue of the metadata for software. And not many people may know that there is a file that you can put in your software called codemeta.json, also citation.cff and a few others, that help you promoting your software. In other words, it helps you discovering. Of course, you need servers for that, and there are services for that help you gathering all of these codemeta.jsons, and you can then browse software. And this is not, of course, not limited to astronomy. This is across many fields. Bruce gave an example because there is a service on CET.org where you can give the URL of your software, And it will then tell you how good a person you've been in promoting yourself. Is there a README file? Do you have this? Do you have that? And so forth. So Bruce described that he was a bit frustrated that the software recognized so little of his software montage. Then Alice gave an example how you can use your code if you have it registered in the ASCL to automatically create a code meta.json and citation CFF. And the purpose of that, of course, is that it makes it for you a template. You can then download that as a simple recipe for that, annotate it, for example, put your emails in them and your magic numbers and so forth and so on. And then at some point, all of these files will be gathered and the software will be discoverable. We gave Jan an invitation to discuss his licensing. So he already gave that summary. Then we discussed, so I'm now at number 5, we discussed the metadata. So this code meta.json has a number of items in it, but you can go deeper and, should the API be in there? Should there be even a better description than currently code meta.json describes? The UAT, which is item number 6, can also be used. For example, if you compare a software paper in the AAS versus that of astronomy and computing, you will discover that the ones in the UAT, which the AAS is using, is a little limited in that sense, and that was discussed. One way to discover better keywords for software is, for example, go to a meeting and do a software census of the people that use the software. And there happens to be a meeting coming up about stellar dynamics and stellar populations, and that would be a nice way to get a better census. We summed up by concluding that it would be good to write a white paper about this with common practices and so forth, after, of course, that we finish the proceedings. And it was also brought up that we should bring up this topic again at the IVOA meeting next week, because this has come up before, but it was sort of discarded 5 or 10 years ago. Ooh, that was a longer summary, I think, than I thought, but that was it. Thank you. And I will try to stop sharing. If that doesn't work, somebody has to steal it from me.
All right. Then we go on Tuesday. Tuesday, we had 3 buffs as well. The first one was, it works on my laptop, how to approach reproducibility in astronomy. Matteo?
Yes. Hello. Let me share the screen. It's going to be fun. Present. Hopefully that works.
Yep.
Okay, just ignore yourselves on the right-hand side. Right, so thank you very much to everyone who attended this both. I think we had a really great discussion. There were some really insightful comments. Opened my eyes to a couple of things and how people can approach reproducibility and what really reproducibility means to different people. So I think, we agreed that reproducibility is important and essential for good science. And I gave the sort of the very extreme example of people that I've spoken with in the past. To them, the idea of reproducibility is having code produce exactly the same results, pretty much to a single bit, every time they run it. And I think the consensus was that this is not really what reproducibility should mean. That at the end of the day, we should care about scientific reproducibility, and no matter where we are in the chain, what we do, whether we see ourselves as a lot of people describe themselves as former scientists or even sometimes failed scientists or former astronomers. We have to remember that at the end of the day, no matter what we do, whether we are software engineers, system administrators, what we do it contributes to scientific results. So this is really the ultimate goal, for the lack of better word, that we are really doing science. So the reproducibility, the scientific reproducibility, is really the key here. But even then, the sort of the low level reproducibility, is important if it significantly changes the experiment results. But as long as the conclusions that you reach from your experiment, from your software, are reproducible, then we're good. And we have to make sure that we enable scientific reproducibility through software reproducibility. There was a lot of talk about current technologies like containers, Jupyter notebooks. There were a lot of comments of, how can you care? One that I really enjoyed was, how can you care about scientific reproducibility if you sometimes have to spend days just installing the most basic software? So I think this is the sort of the things that we have to solve and have a good way of solving that, consistent way of solving that, in order to really focus on scientific reproducibility. And yeah, we need to really recognize the limits. As I said, that comes back to the sort of the first part of, you have to really define of what you expect from your experiment and what you want from your software, from your results, and how would you quantify, what would you really be your threshold for reproducibility? And then we talked about, how we can reach that. And I think there were a lot of comments of how we can, do it in sort of software way, whether with extra scripts, extra checks, whether we could write extra documentation, some white papers. But there were a couple of nice comments that I think really shows the real issue that is, that currently we have with reproducibility, that we can develop the best tools, the best practice guides, but it really depends on us to ensure that reproducibility is followed. I can have the best practice guide, the best white paper that tells you what reproducibility is, but if we don't stick to it, then we're not going to push it forward. It's not going to go anywhere. So we really need to enforce it and start enforcing it. And within our groups, at first you might be unpopular if you create more work for 10 more people. We also need to make sure that the reproducibility is rewarded. So, making sure that it's recognized first, maybe through enforcement, through funding bodies that they require reproducible
One
results.
more minute.
Yeah. And also make sure that, how we approach the reproduced research. So there were a few comments that a lot of papers and a lot of publications and a lot of funding bodies, they only look for original research, and nobody is really interested in, okay, let's rerun this experiment. Let's rerun this simulation. Let's see how it goes, whether we can reproduce it. And we also, there was quite a long discussion on how peer review approaches reproducibility, and I think the key point from there was that things will have to change in peer review and how reproducibility, especially software reproducibility, is approached in the peer review process. Thank you.
Fantastic. Thank you very much. The following one was Jessica, the BOF formerly known as the FITS BOF, and now called Standardizing New and Improving Old Data Formats in Astronomy.
Okay. Is it up? It's up, okay. Yeah, it's pretty simple. So here's the basic, standardizing new and improving old formats. And it's still, we didn't really do this in exactly the order I said, because we had problems getting our FITS expert on, but Lucio Ciappetti talked about FITS, and Rob Seaman talked about PDS4. David Shoup talked about Parquet, which I hadn't heard about until he asked me if he could talk about it. And Perry Greenfield filled us in a little bit on ASDF because he knew about it. And then several people talked about HDF5. So my general summary is that FITS has been sort of stuck for a while, but everybody has there's a consensus about what needs to be done, small changes to make it more useful into the future. the more complicated structured data systems still have formats within them that are compatible with FITs. And if we can make the FITs cover their cases better, then it will require less translation to run a lot of software on that already exists on the data. So one of the things that, despite there not being anything obvious, longer keywords have been, with spaces, have been prototyped in C, IDL, and Java already, which means we're keeping up the FIT standard, which is more than most of the others formats have, of being defined well enough to implement in multiple languages. And we just saw Bill talk about why CFITS.io is the way it is, which is related a lot to why FITS is the way it is. David Shoup talked about Parquet, which is being used at URSA at Caltech for catalogs and tables. And it sounds very interesting. And there's a poster on it, which I probably should have added to this. Then PDS4 is being developed in the planetary data system in NASA's centers for storage and archiving of planetary data, which they all want to be interoperable and intersearchable, much like we do in astrophysics. A lot of it is astronomical data, and some of it is spacecraft data. So they have a lot of different kinds of data, and they're trying to get standards of metadata so it all works, which is challenging. HDF5 has been around for quite a few years as a structured data format with multiple types in a single structure so that you can move it around easier. But there haven't really gotten to be any standards in HDF5 so that you can create one data set, but it's not going to be quite like any other. But the good thing is that the software to access it had been pretty closed, and now it's more open, and it's on GitHub, apparently. And then we finished with ASDF, which is being used by JWST and LSST as a data format. And it's set up to meet their standards, and they talk. It's being semi-independently developed by the two big projects, but they talk sometimes. But I'm not sure, we didn't actually talk about how much they're talking these days. That was an issue at the last couple of data formats, Bob, of getting those two groups to agree on standards for metadata as well as for the formats. And sort of that's where we are going to the future. I think there are going to be some changes in FITS in the next year or two. There's some big, interesting formats coming up, which we'll see more data in. And I think they'll be well enough defined that we can translate data between formats, which is important too. And that's pretty much it. The whole presentation is this brief one, and then the all the view graphs are going to be available through the website, through the ADASS.
Fantastic. That's great. Okay. Thank you. Then we had the last BOF of Tuesday was provenance, practical provenance in astronomy. I don't know if we have people here who want to present it. Okay, we have somebody with their hands up. Francois, I can move you. Well, I will promote you to a panelist.
We have Bruce.
Sorry?
Bruce? Oh, maybe I'm confused.
No, it was the
Providence people would like to talk last, please.
Yes, I want to speak last because we were not aware of preparing these slides, so I'm just finishing them.
Perfect, so, Francois, no problem.
If you don't mind, I will speak the last one.
That's perfect. Then we had a standardization of data formats in gamma ray astronomy. That was Cosimo and Tarek. I don't see them online. We can skip. Then there was a Radio Archives Roundtable. Katrina, you are online here, right?
Yes, I'm here. Just give me a second to share my summary slide. Let's see, here we go. So yes, we had a very lively discussion as well. Very interesting things. Yeah, we started by querying a bit the archives around the world, what kind of data they're serving. Well, the archives of the big radio observatories, what kind of data they're surveying and how they do this. And they told us that many still serve like the raw visibilities, but there's definitely a move towards calibrated visibilities and even science-ready image data. This move is partly driven by the fact that raw visibilities usually take up lots and lots of space. And many of the archives have some type of VO protocols implemented, which is pretty cool because it makes it very easy to query these archives. And two questions that came up in this topic of querying these archives are, how can we write quality measures in the tables to query the data that is there? Like, is there a lot of interference with other sources so that there might be a lot of flagging necessary in the data reduction process, or what's the PSF going to be like? And these things are very hard to predict because they depend on the data reduction process. So yeah, there's a bit of a discussion ongoing how we can give an estimate of these in a way so that the astronomers have a feeling for what kind of data they're going to get. And the other thing is that visibilities are, well, to some degree a bit abstract. They're not yet a finalized image, so it's hard to search them, and it's hard to make them like a, well, I've written useful, but that's more in inverted commas. I guess the thing is, for example, ALMA just gives the visibilities as auxiliary data because it's hard to query them by themselves in a good way, which is also connected to the question how we can properly describe the quality of these data. And so that was one point. And the other point is, given that there's still only lots of raw data available and not always reduced and calibrated data, it would be really cool if small surveys small projects could just upload their data somewhere so that it was available for others, the reduced and science-ready data. And so this is I think a great idea. And yeah, and then we moved on to a bit of a longer discussions, which is again about data formats, and probably would have been interesting for Jessica's BOF too, because there was a bit of a discussion versus we need to use the proper formats for computing because these data sets are big, so you want to parallelize a lot, but then maybe these data formats might not be the right ones for archiving, so there needs to be some compromise to find a good way of doing this. And then we finished with just opening up the question whether radio data providers would be interested to gather for a workshop, talk about how to best or find good ways of setting up nice and useful archives in a collaborative way. And yeah, and then there was also this brief mentioning of backwards compatibility and how some archives have to maintain legacy machines to go back to elderly data and make sure that they can still reprocess this data, work with this data. And yeah, that's something to keep in mind, something that might be difficult for, well, is a difficult question and definitely not solved yet, although in the Discord chat there is an ongoing discussion still how to use containers and singularity and so on to achieve this. So yeah, and yeah, one thing we also mentioned at the roundtable is that next week during the IVA, there's going to be a meeting of the Radio Intes group within the IVA. So everyone who's interested in these topics we discussed at the roundtable might also be interested in coming to this session then. And I think this is all I wanted to say. Thank you.
Thank you so much. Then we had Bruce with a very interesting, well, all the BOFs were interesting, but this also was very interesting, cost management on commercial cloud platform. So Bruce, if you are here, you can just share your screen.
Okay, thank you. I'm ready. I'm going to share my screen. Here we go. There we go. Are you able to see my screen and hear me?
Yep.
Okay, great. All right, so in this BOF, there were 5 presentations on cost management issues in various projects and organizations by Willow Mullane from Rubin, Eric Mitschang from SkyServer, Eva Momcheva from Space Telescope, and myself. I talked about TESS and cloud computing at IPAC. That was followed by 35 minutes of highly energetic and nuanced discussion. And the discussion was nuanced because it reflects the nuances of cost management, which is difficult to do. The costing on all providers is very fine-grained. It can change underneath you with no notice, and the services provided by the big cloud providers nowadays can be overwhelming. The choice can be difficult to make. So I'm going to try and summarize as best I can this discussion. First of all, for navigating the complexities, there was a suggestion that maybe there could be some kind of cost management tools for the community to use, although it wasn't quite clear how that would be done. There was a possibility of holding workshops at national conferences for non-power users. I thought this might be a niche issue that we're talking about, but several people said no, they thought that would be good. Most of the people at ADASS do tend to be of the power user providers. There was a discussion on the best practices. Particularly, you can do things like use on-premise pilot studies to understand what resources you need. You can do your startup using the free tier or the small instances, which are very cheap, and so on. You need to be really vigilant on how your costs are accruing, because this is where you can get into trouble. Eva's talk in particular gave a very useful list of all the things you need to be doing when you're using the cloud and keeping your costs under control. You can negotiate with cloud providers. That's generally easier, of course, if you're a large institution, but also ask for help. Most of us who are giving the presentations had said that they've found that the help provided by cloud companies is really very good. They really do try to be helpful. It was thought that the long-term solution to all these costing complexities is to actually have funding agencies negotiate rates or arrange for credits. I know that agencies in the US are actually starting this effort and hope it comes to fruition in the next year or two. Finally, there was a discussion which was more technical than costing. It's about managing n-dimensional memory mapped files on cloud platforms, which is something that at the moment is very hard to do. Does have an implication for costing, however. If it's hard to do, you could very easily spend a lot of money trying to get that started up on a cloud platform. So that is my summary of the BOF.
Fantastic. Thank you so much, Bruce.
All right.
And the last we have Francois. Francois, if you...
Yes, let me share my screen. So, okay. Can you see the slide?
Yes.
So this BOF was Tuesday evening, the last one, so called Practical Provenance in Astronomy. We started by an introduction to IVOA provenance made by Mathieu. The slides are available. We also had as a starting point the answer to a questionnaire posted and filled by attendants and others before the session. We had a larger number of answers. We also had a starting point, which was 2 days very rich meeting in the ESCAPE project in Europe in September, where we had a lot of use cases presented. And in the conference, we also had 3 posters on provenance, one from CTA, Dirac, one from Vizier and one from Opus, which is also related to CTA. So the discussion was, I would say, not really lively, despite strong interest in the questionnaire. So we were wondering if this was due to the late programming of this BOF, or if we had too much information in the introduction, maybe, we don't know. So anyway, there was still a discussion. So about, for example, providing a specific way of providing minimal provenance, which would be the last step, producing the entities of the data sets we're interested in. Another point was a discussion about serialization and formats. So apparently there is strong interest in serialization in YAML and JSON. Viewtable also, but maybe a little less, and this will require some model mapping on top of Viewtable. There are proposals, as you can see in Vizier poster, for example. But, we had several points about the question of provenance and reproducibility of the data. For example, one discussed point was the translation of data flow languages like CWL and data flow information into IVOA provenance and reverse. People were interested in knowing if we can storing software parameters values used for the activities into the activity representation, and the answer is yes. There was a proposal which is rather new to use code ID to identify software in the activity description. We also had a use case explained where people are interested in finding out data set produced with a given version of software, and actually the IVOA provenance metadata allows to store this kind of information and to find out associated data set or entities to a given version of software. And we also discussed the point of visualization, and some VioProv library outputs were shown, and they are also available in the posters. And so the access using VIO protocols, so for example, ProfSAP and ProfSAP has been evocated, and there will be a DM session, a presentation on this and a discussion in the DM session during Interop next week. So I think that's it, and that's all for provenance BOF. Sorry, we didn't understand. None of us understood that we had something to prepare for this evening. So
that's okay.
Excuse
you did a great job.
Excuse the bad quality of the slide.
That's fantastic. Don't worry. So Stephen, do you want to take it over again as a chair?
So the next thing that we're going to hear from is from Oleg, who is going to talk to us about ADASS 2021, which will hopefully be physically in Cape Town, South Africa. Oleg, are you ready to give your spiel about why we should all go to South Africa?
Yeah, certainly. Can you hear me?
Swan needs to stop sharing.
Let me start sharing.
Very good.
Okay, can you see that? Am I sharing?
Yep, you're sharing.
All right, so I'm coming to you live from an undisclosed location, except I think my fellow POC members have already disclosed everything. So the site of the next ADASS I am now allowed to disclose is going to be Cape Town, South Africa. And here you see an aerial shot of central Cape Town. I can point out the conference venue to you. It's somewhere there. It's called the Westin. I'm not going to show you pictures of the hotel because it's a fairly generic, big, comfortable hotel. It's not about the hotel venue, it's about the surroundings. Here's another shot of Cape Town from a different angle. You can see the conference venue is right there, direct behind that mountain, that bit of mountain called Signal Hill, actually. And I'm going to anticipate some questions from you, and I'm going to answer them. So question number one is, why South Africa? And the answer to that is, why hasn't it happened before? Because South Africa actually has a massive astronomy presence. We've had the South African Large Telescope for a while already. It's a 10-meter class optical telescope. And now there's the new kid on the block, and that's the Meerkat radio telescope. And being a radio astronomer, I will focus on that a little bit more. Meerkat is a 64 13.5-meter dish interferometer with an 8-kilometer maximum baseline. It's the biggest radio telescope in the Southern Hemisphere and the best radio telescope in its band, period. And of course, the 800-pound, 800-kilogram gorilla is the future square kilometer array. This is clearly an artist's impression of the future square kilometer array. Those dishes don't exist yet, but someday it's going to look like this, and it's going to be next to Meerkat on the Meerkat site in South Africa. You might have seen this image before. This was the inaugural image of the full Meerkat, an image of the galactic center. You see these fantastic filamentary structures and supernova remnants and all sorts of fireworks. I prefer this image in this version because I have never seen a president stand in front of an astronomical image before, and suddenly we have two of them at once. Then there's some other Meerkat images for you. These are fairly recent. Some fantastic radio galaxy observations. I'm especially fond of this one because this is a radio galaxy that makes no sense at all. There's no way that lobes of a radio galaxy should be communicating like this, but clearly they are. And in the background is an image of the cosmos field, which shows you that if you're not interested in individual radio galaxies, but if you just want to count galaxies, then Meerkat is going to keep you very busy counting because every single dot here is a radio galaxy, essentially. Another important aspect of the South African program is the human capital development. So there's been a massive effort in building up research and student capacity. And this is a conference picture from last year's student conference. On average, we have around 100 postgrad students and about 30 postdocs in the pipeline at any given time. This is just in radio astronomy. And I think it's probably, in absolute numbers, it's probably one of the biggest radio astronomy programs in the world. I don't know, well, the US might be bigger. In per capita numbers, it's certainly a runaway first in terms of the, number of radio astronomers per capita. You can see some of them are missing their bottom half here for some reason, but that's okay. All their intelligence is in the top half. So yeah, the footprint of astronomy and radio astronomy in particular is absolutely massive in South Africa. We have national legislation that has essentially established a radio astronomy reserve called astronomy advantage areas, and you see them schematically indicated here. In fact, the entire Northern Cape province, this larger outline, is a radio astronomy reserve of sorts. And then you have these designated central areas where the restrictions on activity that is allowed are tighter and tighter until you get to the actual core, which I'm showing here. And the blue dots here are the 64 Meerkat dishes. And then there's a hill and there's the processor building. This is kind of the tightest controlled area of them all. So we are one of the few countries with an actual radio astronomy reserve. Cape Town is down here. Next question you're going to have, isn't it far? Well, it's not as far as it used to be. And the answer is probably not even the furthest ADASS that you have traveled to. Cape Town is served by direct flights from European hubs and from Middle East hubs. And for the rest of the world, you can come in via Johannesburg. You can see that on the map down here. Question three is, will I get mugged, stabbed, or eaten? This isn't an astronomer, this is a sheep. This is a radio telescope, though. The answer is not very likely unless you'd really like to. I reckon Cape Town is not even the most dangerous city and ADASS has been held in. As long as you exercise common sense, you will be, don't walk alone at night, take an Uber, and you will probably find the Uber driver will know about the square kilometer array and will want to discuss your ADASS talk with you. And as far as being eaten, you are far more likely to eat wonderful things because Cape Town has some of the finest and most affordable restaurants in the world. In fact, your top 3 risks being in Cape Town would be, number 3 would be falling off the mountain because you're so captivated by the views. And there's more than 100 ways up Table Mountain, which I'm sure you will find locals to show you. Your number 2 risk is drinking too much wine because there is nearly 1,000 wine farms within a 1-hour radius. And your number 1 risk is you probably won't want to leave. You'll be like Trump in the White House, well, with fewer lawsuits, hopefully. Will you see wild animals? The ones at the top, no. The ones at the bottom, yes. This kind of relates to the will I be eaten question. You will not be eaten because the largest predator in Cape Town is a caracal, and the caracal doesn't eat anything larger than a penguin, I think. You can see plenty of penguins, though. The animals on the top are well worth seeing as well. So if you come to South Africa, I would definitely advise you to book a side trip to Kruger Park and go on safari and see these wonderful animals in their natural habitat. Question 4, what will the weather be like? It's springtime, so typically it's very pleasant weather, sunny and warm, but not too hot for hiking, unless a storm comes in. It's not known as the Cape of Storms for nothing, in which case we'll get horizontal rain. But when bad weather comes in, at least it blows through very quickly. So it should be very nice. Question 5, what else can you do in Cape Town? Well, you can see you can do plenty of things, wine tasting not least. And if that's not enough for you, then you can do all of the above on horseback. Wine tasting on horseback is highly recommended, I find. There's a strange synergy by which your riding improves and the taste of the wine improves. I'm not sure how that works, but as the day goes on, you ride better and better. And of course, the million rand question, what about COVID? What about COVID? I've told you all these wonderful things about Cape Town. What's going to happen with the pandemic? Nobody knows. The dates that we've planned for ADASS is the end of October. So 6 months before, at the end of April, we are going to have to take a decision on whether ADASS is going to be virtual or physical. And of course, what's going to happen until April, nobody knows. We've had some very good news this week about a vaccine, but yeah, really, we're in uncharted territory. So in April, we'll know. If ADASS is physical, then see above, see all the wonderful sites and the wine tasting you're going to do. If ADASS is virtual, then it's probably going to be exactly as this week because Francesco and his team have done an absolutely wonderful job, and I don't think it could possibly be improved on. So I'm just going to give them another round of applause. The only addition we would make to a virtual ADASS, we'd put in some more spectacular Zoom backgrounds. We will organize a virtual wine farm tour, and we'll add a Discord channel for tasting notes for those of us that will be in Cape Town. Because, given the wonderful job that the LOC has done this year, organizing the next virtual ADASS is going to be literally no work at all. We can just take their solution out of the box. So that's great. We'll have lots of time left for wine tasting. Easiest job ever. But I sincerely hope it won't come to that and that we'll be able to actually welcome you in Cape Town physically at the end of 2021. So thanks very much, and I hope to see you here.
All right, thank you, Oleg. And now I'm going to turn the floor over to Francesco, who's going to give some closing remarks.
Okay, so let's see, let's share the screen, hit play. Okay, so it's the end. It's that moment when, it's the end of ADASS. We have to say goodbye, and normally we would be flying home. This year we are already at home, so that's somewhat easier. So I have to say that as the chair of the local organizing committee, I'm kind of glad it's over. That doesn't mean that I'm not sad, but there's also a big relief a big weight off of my shoulder. What can I say about ADASS? Well, ADASS 2020 was different. It was definitely different. You know, we were not meeting in person. We didn't get to show you around Granada. We didn't get to show you this fantastic city, and we didn't get to meet in person. That was definitely the negative part. But there were lots of positive things about ADASS 2020, and I will give you here some numbers. We had a lot of participants. We had almost 600 participants, 581 to be exact. That's a record for ADASS. We were expecting something like 300 had ADASS being in Granada in person. So that's fantastic. It makes me very happy because that means that we managed to reach some people who we would not have reached otherwise, and the people who would not have been able to come here. And these numbers, I think, will raise some more, will increase once we publish all the materials that we have, all the PDFs, all the slides, all the videos, everything, the poster, everything for free for everybody to watch and to read. We'll also keep the Discord server there forever, however, whatever forever means in this world. We are not going to take it offline or anything like that. So hopefully it will be a good resource for people even outside of ADASS. Talking about data flows, we generated 30 gigabytes per day of pixel data. These are the videos from YouTube and Zoom, mostly Zoom because the YouTube is a lower resolution. And one thing that I noticed is that the attendance and the eyeballs on the videos and the presentation was actually really high. The UTC morning sessions were the least popular. The most popular were the UTC evening sessions, interestingly, and in the middle, the afternoon session, UTC afternoon sessions. But when you look at the total views, whatever views means in YouTube parlance, and you add also the numbers from Zoom while the people were watching live, the differences just wash away, which is interesting when you're giving a presentation to an empty room, right? And you're wondering how many people are going to be there. Well, maybe there are only 100 people or so, but wait a few hours and you will get your 500 people without any problem. Anyway, I was blown away by the posters, by the way, all the content, but also the posters. And thank you, Alice. Thank you, Simone, for giving them space, the space that they deserve. Really appreciate that. I think we all loved the video watching marathon. That was really cool. And the lightning talks were fantastic. But mostly, I have to say that ADASS was an amazing conference. Because of you, all of you, you all made it possible. ADASS is a community conference for the community, by the community, and it's great because we have a great community. So I first of all want to thank you all for making ADASS this fantastic conference. I also want to obviously thank the local team, almost local. Anna Carla is actually not here in Granada, but everybody else is in Granada, locked in their own houses. So, so I want to call their names. This is when in in-person conference they will be joining me on the stage, but we can do it next year, I guess. So Jose Enrique, Alicia, Anna Carla, and Angela, thank you so much. You have done an amazing job. Jose Enrique in particular did an amazing job and an amazing amount of work during and before the conference, but thank you all, folks. ADASS 2020 would not have been possible without you. Absolutely, thank you. And I want to finish now with some hope. You know, we will be back next year. I really hope to be in Cape Town, drinking that wine and trying that food and watching some more amazing presentations. And in the meantime, with my finger closed there, don't forget your proceedings. The deadline is December 6th. So please upload them to the FTP site. If you gave a talk, it would be cool if you could upload your slides to the FTP site. A lot of people have done it, but quite a number are still missing, so that we can publish everything, everything we have. And with this, I thank you. I give the microphone back to, I stop sharing. I give the microphone back to Stephen. And I thank you again for this fantastic conference.
Thank you, Francesco, for this talk, and thank you for organizing ADASS. It has not been easy, and I'm impressed by your energy. Every time I see you, even though it's like 3 o'clock in the morning your time, you still seem to have all kinds of energy. You said yesterday that you're going to, start a week-long hibernation. I believe that, but up until now, you've just been doing an absolutely amazing job. I have taken the unprecedented step of allowing all the participants to talk, and I would like all of you to unmute yourselves, and none of this, pre-recorded applause. Let's everybody give Francesco an enormous hand for the work he's done. Thank you very much.
Go!
Well,
Give a standing ovation, but then you just be looking at, yeah, that won't work.
The applause goes to all the local team. I could not have done it by myself. Not even trying, right? It would have been impossible.
All right. That concludes ADASS 2020. Thank you all for attending, and hope to see you all in person or online at least next year. Goodbye.
Thank you.
Bye, everybody.
Goodbye, guys.
Bye, everyone.
Bye.
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 Bye, everyone.
Everyone.
Farewell.
Thank you.
It's like people really have to go someplace. I'm going to hang out on Discord.
I'm gonna have lunch.
Bye, Alice. Bye, Alice. See you.
Bye-bye. Thank you so much for everything.
Bye-bye. I became addicted to this kind of meeting.
Thank you, Francesco. Bye.
Thank you, everybody.
Okay.
And the Jose too.
Yeah, thanks, Francesco. You and the lab did a great job.
Thank you. We appreciate it.
Hopefully we'll do real hugs next year.
I guess we all hope. Yeah.
And share a couple of real drinks. Thank you very much for everything. It was an amazing conference. See you next year.
See you all next year.
Yeah, Alex and I will take you out and the log if they appear if we meet at the Cape Town, take you out for wine or beer or whatever you want.
Thank you.
That's right. She and I both have it in writing for the others, so we're committed to it.
Yeah, 2 of us at least.
Awesome. Looking forward not only to that, but to that as well. Cool. Well, we'll leave the Discord on forever. We'll publish all the material before the end of the year, and hopefully we will see you live in person in Flesh and Bones and in Cape Town.
I hope you get some rest.
Yeah, sleep well. Okay, I'm going off. Bye.
Bye.
Bye bye.
Everyone.
Bye bye.
So Francesco, I don't think everybody's going to leave until you close the session down. Everybody doesn't want it to end.
Too right.
I think so, yeah. Well, folks, the conference is officially over. See you next year.
Okay.
Bye.